I'm going to hit record now so that we have a record of this. This is our final class before the exam. We're going to do a homework today. We're going to do a lecture, and we're going to have a lab. I'm not going to try to do the inverse square law again because the equipment here just wasn't working right. I will probably try spectroscopy, but I don't think I put it up yet. So during our micro break, I'll throw up spectroscopy so you can download the sheet. I should have the materials for it, and it's a decent lab. So why don't we get right to it so we don't waste any more time. And let me go to speaker view and grab something, and then we'll, do you guys have the question numbers ready to go?
Yeah.
Okay, hold on a sec. Which homework number is this? Is this 5 or is this, I think this is 5, right?
4.
Oh, really?
You don't have 5 posted. You have 6 posted.
Oh, okay. Sorry, things are a little chaotic over here. The homework we should be doing is the one that's chapter 5. Is homework number 4 the chapter 5 homework?
Yes.
That's good.
Yeah, it's at the bottom of the screen there on Blackboard.
Okay.
It's not numerical order, that's all.
Well, I'm looking at you guys right now, so can you read me the problems? Chapter 5.
43.
Yep.
52.
Yep.
54.
Yep.
56.
Yep.
And 57.
Don't worry that we're starting a little late today. From what I remember, this homework is much more gentle on the system than the last one was, which had many, many parts. Okay, so Joel, since I've got you talking to me, would you be kind enough to read us the title and the words of chapter 5, number 43?
All right. Part A, the most common form of iron has 26 protons.
Oh, sorry, what's the title? Is it just about atoms?
Oh, atomic terminology practice.
Okay, so this is part A. The most common form of what element?
Iron
Yep.
has 26 protons, 30 neutrons, and it wants us to state the atomic number, the atomic mass number.
I call that A. And then the mass number, which I call, not everyone uses these symbols, but I like them because they're simple.
And it wants to know the number of electrons if it is neutral.
Okay, I think we can handle that. We did have a discussion on atoms last time, correct?
Yeah.
So I would expect, even without my help, you guys would probably know the answer to these, right? Someone should. Anyone?
The atomic number is 26.
Yeah, Evelyn, how'd you know that?
The atomic number is the number of protons.
Correct. So we'll even write that afterwards. You usually don't have to put units on it, but we're going to put units for helping so that we help remember for ourselves. Remember, this is not just a homework, it's a nice study guide. And the mass number then?
56.
That's right. I want to address something really quick about the mass number that is maybe worth mentioning. If you go and look at the mass number on a periodic table of elements, instead of the mass number of iron being 56, let's see if I still have that here. Fe is the symbol for iron. You guys will notice that on this periodic table of the elements, the mass number of iron is not listed as 56. The atomic number is still 26, but the mass number is listed as 55.933. Now, this is supposed to be the number of protons and neutrons combined. Why would it be fractional? Why is it 55.933? Can you have half a neutron? Or this is a question to see if anyone's taken chemistry and remembers what the deal is. I think it's something worth knowing as a student. No? Not sure why they did that, huh? The standard form is to not give you the mass number of the most common isotope, but to give you an average of all the different isotopes and to weight them by their, do you remember how I talked about the cosmic abundance of deuterium? What was the cosmic, we need to remember the cosmic abundance of deuterium to understand my argument. What was the idea behind the cosmic abundance of deuterium? You might want to just fresh your mind up with your notes.
$6,000
Yep.
hydrogen is equal to 1 of the deuterium.
Yeah, and I didn't mean to say equal. Well, equals is fine. I put a colon there, but the idea was there's a ratio. And the ratio is you get 1 deuterium for every 6,000 protiums or regular hydrogens. So let's take a look real quick at the mass number for hydrogen. Can you guys see how it's 1.008? That's an average of the 6,000 protiums, and the 1 deuterium slightly increase, the average atomic mass comes out to be slightly more than 1 because you get a small amount of deuterium for every hydrogen. What this mass number here tells me when I see 55.6, that tells me that the most common form of iron is iron 56, which has 30 neutrons. But the fact that it's slightly less than 56 tells me that the next most common isotope of iron is probably something called iron 29, which has 1 less neutron. And that's probably also around, well, other atoms are made from the fusion in stars, as we are going to come to learn, but probably the nuclear processes in stars occasionally create different isotopes. Okay, I don't know. I thought that was interesting, but maybe not. How about the number of electrons if it's neutral?
$26.
Yeah, that's right. Okay, move on to B. Oh, you know what I need to do? I need to move yesterday's lecture so that my disk has enough room for today's lecture. Yeah. Sorry, I wanted to do that. One thing I'm terrified of is running out of disk space while we're recording. Let's get that going. Paste. Okay. Okay, continue.
All right. Part B. Consider the following 3 atoms. Atom 1 has 7 protons and 8 neutrons.
Hold on a sec. 7 protons and 8 neutrons. Yep.
Atom 2 has 8 protons and 7 neutrons.
Okay.
And atom 3 has 8 and 8.
8 protons, 8 neutrons. Okay.
Which 2 are isotopes of the same element?
This should be pretty straightforward, I think, given our just recent discussion of isotopes. Which of these 2 are isotopes? Really? Because I was just talking to you guys about isotopes, right?
1 and 2,
No, that's not how it works.
or 1 and
2.
3.
2 and 3.
1 and 3.
two and three.
Oh, I'm screwed.
Because
Oh, yeah, no, that's
because
what I
they
meant.
have the same atomic number.
Yeah,
They have the same number of protons.
got
But
it,
it's-
got it.
Remember, the number of protons defines your atom, right? So I know that these two have to be the same atom. The differing number of neutrons represent the different ratios of isotopes. You know, like neutrons, you can, you know, something we didn't talk about last time, and maybe this would help to put things into context. What does a neutron do in an atom? Does anyone know? Where's my little atom picture? What are these little neutrons doing inside of an atom?
Stabilize it.
They are stabilizing. Why would you need to stabilize the nucleus?
Because it's so
Well,
because of the charge.
yeah, charge. Now, how does the charges
Because
work?
the electromagnetic field, or something to do with
Yes, yes. The electrons are really far away from the nucleus. This picture makes it look like they're just a block away. But if you draw the atom to scale, the electron orbit is millions of times larger than the diameter of the nucleus. So the electrons are way, way out here, and the nucleus is in the middle. And the nucleus is full of positive charges. Now, when we learned about the force of electromagnetism, we learned that positive charges or like charges will all repel each other. According to the laws of electromagnetism, this nucleus should be trying to fly apart from its own positive charge. And therefore, atoms should not be stable and the universe would cease to exist, at least matter would. But of course, that's not the universe we live in. Matter seems pretty solid and stable. How does it achieve this stability? There must be another force, something different than electromagnetism, that's gluing all these angry positive charges together and keeping them from disrupting. That's the neutrons. The neutrons are a type of nuclear glue that glue the atom together. They glue it by the strong force of nature, which to this day is still one of the more mysterious of our four forces. And we're not fully entirely sure how it works. But we do know from observation that in the same way that sometimes you can add a little too much glue or sometimes not enough glue to something that you're trying to stick together, nature will sometimes have an extra neutron or missing a neutron. Usually the rule of thumb is 1 proton for 1 neutron, but as the nuclei get heavier and heavier and heavier, you'll often see atoms that need more neutrons than protons to glue it together. Anyways, the point being that once you have a certain number of protons, usually you want an equal number of neutrons, but sometimes you can add a few more or take away a few more. You'll notice, for instance, in the case of iron, which we just dealt with, the most standard form of iron needs an extra 4 neutrons to effectively glue the nucleus together. It's not just 26 protons and 26 neutrons. It's a little extra. Okay, anyways, these two are isotopes. I'm feeling long-winded today. I should probably cut that out. Damn me, always trying to teach you something.
It's good.
All right. Okay, how about part C?
Oxygen has.
I'm sorry, wait, before you go, did I finish that? Answering that? I mean, was there any other part? Okay, yeah.
No, it was just what two are isotopes of the same element?
All right, cool.
So part C, oxygen has atomic number 8. How many times must an oxygen atom be ionized to create O+5 ion? How many electrons are in O5 ion?
So an O+5 means it has a net excess charge of +5. And do you guys, part of this question is just to see if you remember what ionized means.
Is that where they have the extra electrons?
Or a dearth of electrons. Extra means you gain some, and that is an ion. But more frequently, when we're talking about atoms, we consider how they are getting electrons torn off of the atom. How many times did they ionize this oxygen atom?
5 times.
Sorry?
5 times.
Correct. So they had to ionize 5 times ionized. And how many electrons are left? Is that obvious, or?
5 less.
What if
5
Sorry?
less than
Sorry, Joel. what?
3.
Yes.
3.
Oh,
I was trying to do math with a number I was spacing out on.
there. Can I just go through some notation for you guys? When you don't feel like writing
Sure.
electron, the symbol for electron is a lowercase e with a minus. It's kind of like a shorthand for electron. So we'll use that here. 5 electrons left. And that teaches you some notation while we're at it. And I think that's the whole problem, isn't it?
Yep.
All right, so that's a nice, it helps you review some of your fundamentals of atoms. That's useful, I think. Probably ask you 1 or 2 questions about atoms on the exam. By the way, at the end of class today, we can spend some time talking about the format of the exam and our plan for office hours that day. So let's not forget to do that. I'm going to erase. Well, let me give you everyone a second here. Everyone looks good, I guess. Let me scroll your faces. All right, I'm going to erase here. Yep. Sarah, you good? Okay. Let's do the next. I really enjoy these problems because they're short and sweet and kind of fun. So chapter 5, number 52, what happens there?
Human wattage.
Oh yeah, this is a fun problem. Before you get going, in our last class, I was trying to do a bunch of things at the end, and I didn't cover every single thing as usual. The one thing I didn't cover that we need for this problem is a simple concept. There is an idea called power in physics, and power is defined as energy divided by time. So I'm going to say this again in lecture today, but let's just put this out here. Energy divided by time is an energy flow. Let me ask this question. What are the units of velocity in the MKS system?
Kilometers.
That's distance, kilometers. What about velocity? And by the way, in the MKS system, it's meters.
Of course, that was what I said.
I love it. That's my line. What about velocity? No? No one knows the units of velocity?
Is it joules? But that's not
That's
really
energy.
Oh.
Seconds?
Cameron, meters per second squared is an acceleration, but I'm asking about velocity.
Meters per second.
Meters per second. Okay, you got it. Now, don't take this down. This is just scratch paper right here. If a distance is measured in meters and a velocity is measured in meters per second, do you think those are like the same thing? They both involve meters, but wouldn't you agree that those are wildly different concepts? On the left, you have a distance. This is a meter, right? This board is about a meter long. But a meter per second tells you how fast something is moving, like a skateboard. You might think of velocity as being a distance flow. It's a flow of distance. By the same token, energy is not the same thing as power. Power is energy per unit time. It's an energy flow. It's a rate that energy flows through a system. Power can be quite abstract. Now, let's review the MKS units of power. Normally, energy is measured in joules, and time is measured in seconds. And in the MKS system, we define a joule per second as a new unit called a watt. So I know you guys have heard of wattage before because it's hard not to in your everyday life. A light bulb that's an LED light bulb might have 30 watts. An incandescent light bulb might be 60 watts or 80 watts. And your hair dryer might operate at 100 watts. A guitar amplifier might be 250 watts. You know what I mean? Wattages are not energy. They're a rate that energy flows through a system. And that concept is called power in physics. Okay, Joel, now, or whoever was reading, let's try that again. Oh, by the way, the point of this problem is kind of interesting. Remember how last class we learned that calories are a form of energy? Well, most of you know from living your lives that there's a calorie requirement for a human of around 2,000 calories per day or so. Calories per day is also a wattage. And that means you are, in a sense, kind of like a light bulb. You have a certain energy flow requirement to maintain daily operations. Okay, Joel, take it away.
All right. So a typical adult uses 2,500 calories of energy each day.
I wonder, are those kilocalories or regular calories?
Regular calories.
Well, I don't know if regular calories to you means the same thing that regular calories do to me. You probably mean by regular calories, your food calories that you see on a package. For me, the regular calorie is the British calorie of 4.2 joules. Do you guys remember this issue?
Oh, yeah.
So the British calorie, the original, see, my calorie, the real calorie is the original calorie. The original calorie is 4.2 joules. But a kilocalorie, which they sometimes lamely just use a capital C for, is 40.
Oh, yeah.
I think they're referring to the kilocalorie here.
Yeah, it's a big C.
All right, okay.
I forgot about that designation.
All right, okay. Yeah, I just wanted to clear that up in case we get forgetful. So, okay, so 2,500 calories per day.
So use this fact to calculate the typical adult's average power requirement in watts.
In theory, this should be doable. How should we begin? What do you guys think about this? If only I had
somehow do dimensional analysis, but
Hell
I
yeah.
don't know the conversion.
That's almost always the answer. All right, so how do we start then, Joel? If we're going to do dimensional analysis, how would we start it?
Just said I don't know the conversions.
Huh?
So
I just said I don't know the conversions.
Well, look, man, you got to romance me before you take me upstairs. But before you get to the conversions, we have to know how to begin this.
Laura
right?
was going to chime in, I think.
Oh, okay, yeah. Laura?
So we're going to write down the number to convert, which would be 2,500 big cal per day.
Great. That's what I was thinking. So we have to start somewhere. Let's start with 2,500 calories per day. Okay.
And then multiply by the division bar.
Okay.
And then put the units to cancel. So
Now
when
gotta
we
start-
do, because we want to go from big cals to joules and then from day to seconds, right?
Pretty much, yeah. Yeah, I would say that's a pretty good statement of the problem.
So how do we know which one canceled first?
It's sort of a free-for-all. You can dice your onions and then the potatoes, or you can dice the potatoes and then your onions. It's up to you. They're all going in the same stew.
Okay. So let's do big cal on the bottom.
Okay.
And then to joules on the top.
Yep.
So what were you gonna say?
Oh, I'll let you go.
Okay. 4,200 joules on the top and 1 cal on the bottom.
Yep. Beautiful. So now we have joules per day. That's our current setup. With calories gone, we're now working with joules per day.
So if you multiply that, it's 1 times 10 to the 7 joules per day.
Whoa.
No, did I do that wrong?
Yeah, you did it wrong because we're doing dimensional analysis here. So now we have another division bar, and we need to keep focusing on units first, right?
Okay.
The short,
So-
you want to know the Cliff Notes version of dimensional analysis? Units first, numbers second. That's how we should be thinking. Units first, numbers second.
Okay. So now what do we do? How do we get rid of the day though? That's what I'm
That's a
confused.
damn fine question. I was hoping you'd figure that out. That's kind of the fun of this. How do I get rid of that day? You do it like you would with any other dimensional analysis. What's messing you up right now, Laura, is you're not used to seeing the unit on the bottom. But I assure
Right.
you, you can deal with it in the same manner.
If you put day on top
Very good.
and then hours on the bottom.
I think to get to watts, we're going to want to get towards seconds. Oh, no, you're right. I'm sorry. Wow, I'm dumb. Yes, what Joel said. Okay.
I don't do math that fast, Brendan. I can't do 24 times 60 times 60 in my head.
No. I was just that you're heading in the right. For a second, I thought you were heading towards a larger unit of time, but you're heading towards smaller units of time, and I am happy. I'm just a little, shall we say, shaken, not stirred this morning. Okay.
So it'd be 1 on top, 24 on bottom.
Okay. And now?
Then we can do hours on top. And then
Minutes.
Yep. I was going to suggest because
well, we can do seconds.
Do you know the number of seconds in an hour?
3,600.
Then that's valid. I was going to say let's take a shortcut and figure out the number of seconds in an hour. Normally we would go to minutes and minutes to seconds, but since Joe knows that 1 hour is 3,600 seconds, I think everyone's probably cool with 60 times 60. So that was a little shortcut. We kind of smushed 2 steps together, but little shortcuts are okay. I had a great moment in yesterday's lecture where I was doing dimensional analysis with the class, and this girl was converting from seconds up to years. And so I said, well, do you know the number of seconds in a day? Expecting her to say no. And she just busted out with whatever it was, like 84,600. And I was like, you know that from the musical Rent, right? And she was like, yep. And I was like, okay, well, that is valid knowledge. If you memorized one of the songs in the musical Rent, and now you know the number of seconds in a day, I can't stop you from knowing that conversion, and that's a valid conversion factor. So sometimes you can learn conversion factors in unlikely places. Why don't we go ahead and we're going to do, so let's check out the program. Multiply this times this, then divide by 24, then divide by 3,600. And that should be our man.
$122 joules per second.
By the way, it's 86,400. I backwards those 2 numbers. I'm sorry, what'd you get?
122 joules per second.
Let's just make it 120 joules per second, because I think we're at the 2 sig fig level here. And how do we convert this into watts? That's kind of a trick question.
You just put 120 watts.
Yeah, exactly. Okay.
Or W.
I wanted to make sure that you guys understood that a joule per second was a watt. So basically, you're operating at roughly the same power as an incandescent light bulb. Your energy requirement is similar to that of a light bulb. And as you will learn in today's class, you actually glow like a light bulb, just not at visible wavelengths. Okay, I'm ready to start the next one. I'm erasing.
All right. Let's see. Number 54.
Okay.
It's radio station.
Oh yeah, this is a fun one. Now, at the end of last class, I gave you guys 3 formulas. And so, was it radio station or radio photon? I guess.
Station.
Okay. As a preamble to this, last class I gave you 3 formulas. I think we should write them down over here in the margins because we're going to want to use them. The first formula is the speed of light is equal to wavelength times frequency. The second formula is that the energy of a photon is Planck's constant times frequency. And the third formula, which is a combination of 1 and 2, it's an additional extra formula, is Planck's constant times the speed of light divided by the frequency. Now, these formulas are easy and fun, but you haven't gotten to try them out yet. I introduced them in lecture, thank God, but I haven't gotten to try them out. What I would like to point out is that several of these variables are constants of nature, namely the speed of light and Planck's constant. If I draw this, does that look brown to you guys? Probably not. That probably just looks black.
No.
Let me find a more advanced color here. I'm going to do something. I'm going to change the colors of the constants of nature. I'm going to do that so you can see where the variables are. So C, the speed of light, is a constant. And H, Planck's constant, is a constant. And if I use color to my advantage here, this ought to help you guys see the relationship between the variables. The variables are here, 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 and there. And let's write down our constants of nature. The speed of light, C, is 3 times 10 to the 8 meters per second. And Planck's constant is close to 7 times 10 to the negative 34 joules times seconds. The constants of nature are interesting, but we'll deal with them later. Okay, Joel, give us the setup. Oh, by the way, let's draw a picture of the setup. I'm going to draw a radio tower, okay? So let's sort of draw the superstructure for this thing. And we'll have a blinky light. And then emitting from the radio tower is going to be a big-ass radio wave. It's an oscillating photon. Remember that radio waves are a form of light. They're an electromagnetic wave. So they're similar to light, but they're just light at a different wavelength. Okay, what are the givens, Joel?
All right. What is the wavelength of a radio photon from an AM radio station that broadcast at 1120 kilohertz? And what is the energy?
So we have 2 jobs. Find the wavelength, whose symbol in physics is the Greek letter lambda, and then to find the energy. The first thing I want to address is the given. What type of quantity is this? What would we call this? 1120 kilohertz.
The frequency.
Thank you. And that's something that might not have been obvious to everyone. This is a frequency. So let's say equal to F. We want to understand that we've been given a frequency here. What are the typical units of frequency? What are the standard MKS units of frequency? This you may need to consult your notes for.
Meters or kilometers?
Cycles per second?
Cycles per second. But a cycle per second, Evelyn, is also known as a...
I'm not sure.
Okay. Let's write this down. Huh?
A hertz.
That's right. So
Yeah.
units of frequency are cycles per second, or 1 over seconds, which are the same as hertz. But Evelyn, notice that we weren't quite given hertz. We were given kilohertz. I bet knowing the metric system as you do, you could figure out the conversion from kilohertz to hertz, couldn't you?
1 hertz is 1,000 kilohertz.
1 hertz is 1,000 kilohertz?
Other way around, other way around.
Yeah, exactly. Kilo should be the big one.
Yeah.
1 kilohertz should be 1,000 hertz. So 1120 kilohertz is how many hertz then? Can you do that in your head?
112,000? No, 1,120,000?
Right, or if we put it in scientific notation, 1.12 times 10 to what power?
To the 1, 2, 3, 4, 5, 6.
Good. Okay, this is an MKS unit. We can work with that. Now our job, so we had to just, I wanted to get out of kilohertz and get into hertz as quickly as possible because that's what our formulas are going to require. Now let's focus on the wavelength. Which equation, 1, 2, 3, would we best use here?
One.
Yeah, because we are given the frequency, and this formula will allow us to get to the wavelength with only a constant in between. Laura, do you have the chops to rearrange equation 1 to solve it for wavelength?
Wavelength equals C over F.
Right, so I want to point out what she just did there, class, because not everyone's got the same algebra skills. She wants to solve for wavelength. Wavelength is on the right-hand side, but at least it's on the top of the equation. So she simply takes the F and flips it down to the bottom over here. C divided by F. That's good algebra. I'll flip the whole thing around for her. Wavelength is equal to C divided by F. And I'm still trying to be helpful here, so I'll use blue. C, of course, is 3 times 10 to the 8 meters per second. And our frequency is 1.12 million hertz. Here, I'm going to supplement hertz with per seconds so that my units will work out.
$268.
Let's 2 sig fig that. Well, actually, Evelyn, I didn't tell you this, but the 3 times 10 to the 8 is weirdly good to 3 sig figs. So I take it back. You can keep 3 sig figs because this has it as well. So let's go with 268 and the units.
Oh, the wavelength.
We'll just look at your unit balancing here.
Meters per second squared.
This is the bottom of the top. This is the bottom of the bottom.
Like this thing, I was forget how to do it. It's just meters then.
That's right, because the bottom of the top is the bottom, but the bottom of the bottom is the top. And therefore, you can just think of it as the 1 over seconds cancel out. Okay, we've just done the wavelength. Now it's time to do the frequency. I'm sorry, now it's time to do the energy. Which formula should I use to get the energy?
The second one.
Great, because we have the frequency and that will give us the energy.
And we can keep it simple.
Yep, I like it. I like it simple. Okay, so E equals HF. H is 7 times 10. I didn't use blue, sorry. 7 times 10 to the minus 34 joule seconds times 1.12 million cycles per second. 8 times 10 to the negative 28. Negative 28. 8 times 10 to the minus 28. What is it?
That's weird.
What?
I got 268.
No, that's here. Wait, Joel, I think you're doing this, but you should be doing this, right?
No, I did E equals H times that.
That's impossible.
That's why I said it was weird.
Well, try it again.
7 exp 34 Yeah, that's way off.
Are you still getting the wrong answer?
No.
Okay.
Well, I got a different answer this time.
Let's keep two sig figs.
7.8 times 10 to the negative 28.
What are the units?
Joules.
Very good. This is a very small energy. All right. Nicely done. This will be a great study guide. I'm probably going to make you do some wavelength, frequency, energy calculations in the test. So pay attention to how we're doing all this. How's everyone doing? Can I race? Jose, you good? All right. I'm racing. What's next? I'm going to leave these three equations up because I think they're going to be helpful for the next problem or two.
All right. 56.
Okay. And what's this one?
X-ray photon.
Okay. Hit me.
What is the wavelength of an X-ray photon with the energy 10 keV?
KeV is how they say it sometimes. It's kilo electron volts, but most people just say KeV. There's more to the problem.
Yeah. What is its frequency? Yeah, that's it. But it gives 1 EV equals 1.60 times 10 to the minus 19 joule.
Right. So I'd like to make this a choose your own venture to see if you guys can handle it or not. I know you've only recently learned these formulas, so this might be asking a lot, but if I took the training wheels off for a second, would you guys know how to get going on this? What do you think we should do? I'm intentionally not giving you a lot of instruction because I want to see how the class does as a collective unit. I gotta say, guys, we're really killing this one. We only have 2 problems left, so we might get a nice little break before class, which is good because I need to put up your lab. But since we've got a little extra time, let's kind of pretend this is the test for a moment. I'm not here to help you out like I normally am. What should we do? Let's focus on our goals. We have to get the wavelength and we have to get the frequency.
So we can't use the first formula because of the unknowns.
Frequency. Okay, that's a good point. That's a good observation, Joel. With that in mind, What's your thinking then?
Could you convert 10 kilojoules into joules and then use
That's a good, your thoughts are good, Evelyn. My only complaint is those are not 10 kilojoules, they're 10 kilo electron volts. So do you want to rephrase that?
convert the 10 kilo electron volts into joules?
Yes,
Yeah.
we do want to do that. Let's start there, Evelyn. So Evelyn, by the way, Joel was doing the right thing because he was working backwards. He was going to look for the formula. The formula eventually is going to lead you to the energy. But then Evelyn was jumping to the next step and saying, well, if we're going to work with energy, we're going to need to be in joules because we always have to get our units into MKS form. So she's on the path here of what we should start doing. So let's start, Evelyn. Help us do that with dimensional analysis. What do I write down?
10 kilo E. I forgot what that is already. KeV.
You can just say KeV. They're electron volts, but KeV.
Yeah. 10 KeV multiplied by a division bar.
Yep.
And put KeV in the bottom.
Yep.
And EV on the top.
Yeah, we got to go to EV first because our conversion is EV to joules, not KeV to joules.
Yeah.
But what, now, Evelyn, this sounds like the last question I asked you, but what do you think the conversion is between KeV and EV? No, in your metric system.
1 EV is 1,000 KeV. Or the other way around?
Yeah. I was curious to see if you could catch that error on your own. It should be that the EV's 1 kilo is 1,000 regulars, right?
Yeah.
All right. I hope the rest of you are following what she's doing here. Okay, and now what?
Do another multiply by another division bar. Do 1 EV on the bottom and joules on the top. One on the bottom and 1.6 times 10 to the negative 19 on the top.
I like it. Oops. I like it. Okay, punch them up. Everyone should be punching. Don't just copy, but you have to punch. Every time you punch that calculator, it's like training for your fingers.
.6 times 10 to the negative 5 joules.
I got negative 15.
Yeah.
I got negative 16.
I'm sorry, guys. I have a frog in my throat. I needed to get a little water. What did you get?
I got 1.6 times 10 to the negative 5. But everyone else
Negative
did.
5.
Yeah, I must be doing something.
You want to know how I fact check that, Laura?
Yeah.
10 times 1,000 is 10,000, right?
Yeah.
And 10,000, what is that in scientific notation? 10,000. 10,000 is 10 to what power?
To the 4.
And if I add 4 plus 19, negative 19, and I add 4 to
Negative
it,
15.
so there's no way it can be 5, right?
Yeah. So what am I doing wrong? Because I keep getting that same thing.
Maybe it's not clear. Maybe my writing isn't clear on your screen.
Oh, you know what? I know what I did wrong. No,
Okay.
I did it wrong. Never mind.
In fact, I hate to say it, but I already know what the answer is. It's 1.6 times 10 to the negative 15. Because I can see that I'm just going to add 4 zeros and the lead digit's going to stay the same, right? I don't even need a calculator for this. I'm so damn good. 1.6 times 10 to the minus 15. What are the units?
Joule.
Yeah. Now that's just the energy. All we've done is convert the energy. So now, Joel, you were having a big thought just before we went on this trip here. What was your big thought?
Use Formula 2.
I agree,
Because
Joel.
because we have E, which is the joules, and then H is a constant.
Correct. Now, why don't you try your hand at rearranging this formula, because that'll be an interesting exercise. If I say frequency is equal to, what should be the letters on the other side?
E over H.
Excellent. I love it. Okay, so now we're going to plug in our E's and our H's. The E is 1.6 times 10 to the minus 15 joules. The H is 7 times 10 to the negative 34 joule times seconds. Seven times 2 is 14. So this should give us something close to 2 times 10. Punch it before I can do it. Let's see, 34 plus 50, 15 plus 34 to 0. Positive 19. 2 times 10 to the 19. 2 times 18. Let's do 2 sig figs. 2 point something.
2.3.
And the units?
Seconds.
Seconds are in the bottom, Joel.
Per second.
Per seconds.
Yeah.
Which is the same as 2.3 times 10 to the 18 hertz, right?
Yeah.
All right. That makes sense. Remember, if the seconds are on the bottom, you got to pay homage to that.
Yeah.
We've got the frequency. Now we got to handle the wavelength. Which formula do I prefer for wavelength? You've got 2 options here.
The first one.
Yeah, that's simple. Okay, and that means wavelength is equal to what?
C over F.
Good. The speed of light is a constant, 3 times 10 to the 8 meters per second. The frequency is, hey, do you think we should use per seconds or hertz here?
Per seconds. So
yeah, that's better because it'll cancel better. See, 3 divided by 2 is 1.5-ish. 8 minus 18 is negative 10. 1.5 times 10 to the minus 10. How did I do?
1.4 or 1.3 times 10 to the minus 10.
Okay, I was close. I assumed that 3 over 2 is 1.5, but it's 3 over 2.3. So you said 3?
Yep.
And the units?
Meters.
Meters per second. Oh, never mind.
No, that's meters. By the way, can I just ask for a style point here? Today, you're going to be learning a lot about light. And a customary thing to do when you work in light is if the wavelength gets stupid tiny, like 10 to the minus 10 meters, it's customary to convert it to a smaller unit like nanometers. And I think we should get in that habit. 1 nanometer is 10 to the minus 9 meters. It's a billionth of a meter. So let's try to convert that next to nanometers. Meters on bottom, nanometers on top, 1 and 10 to the minus 9 on the bottom. How many nanometers is that?
$13.
13 nanometers. That's kind of classy. Wait a minute. No, Because that's 1.3 angstroms. An angstrom is 10 to the minus 10 meters. And an angstrom is smaller than a nanometer. So that can't be 13 nanometers. We had to have done that wrong.
I got 0.013 nanometers.
That's because you typed in 10 exp minus 9.
Oh,
You
you're
typed in 1 exp minus 9. Remember, 10 exp minus 9 is actually 10 to the minus 8. Do you get me?
yep, yep.
So it should be 0.13 nanometers, right? And I know that because that's 1.3 angstroms. Y'all buying that? I'm not sure if I've convinced you guys of that. This is an extra move just for class, okay? This is a classy thing to do.
Makes us look really smart.
Yeah, exactly. You'll notice, for instance, well, I'm fascinated by X-rays and gamma rays. They're just cool parts of the electromagnetic spectrum. In today's lecture, where we're going to begin, I think it's slide 86 maybe, or maybe, no, it's 65, somewhere around here. Here we go. So these are all the different types of photons that are possible in nature. This is like the periodic table of the elements, except for light. This is a very important graph, and I'm going to tell you guys right now, because it's so important, this graph in our class, that I might as well just spoil the surprise and tell you that this graph is going to be on the test. I'm going to ask you to memorize this, okay? So let's get started on it. Our photon that we just calculated, 13 nanometers, sorry, 0.13 nanometers is right about here. That's where it was. Just past ultraviolet into the X-ray spectrum. Actually, hold on, this is logarithmic. If that's 100th and that's 10,
that'd be
kind of in the middle.
gammas.
No, gamma
no,
doesn't
no.
start until 100th of a nanometer. So gamma, not until you get
I'm
to
not good at
100th.
math today. Leave me alone.
Okay. I'm feeling a little, I feel a little
I'm
wiggy.
having an off day with numbers.
Yeah, me too. Cool. All right, we got one last problem to do. Let's crank it out, and then we'll talk about stuff and take a break. Can I erase? Does everyone have stuff? No objections, right? Have you guys ever gone to the light bulb section of Home Depot and seen those colored light bulbs, the party bulbs as they were?
Yeah.
They're kind of fun. In my studio, I've got a lot of party bulbs because colored lights are fun. I must be like a real simpleton or a rube because I like colored lights. You know, they make me happy. And sometimes you can get one of these Home Depot party bulbs. They have orange ones. So it's just a light bulb colored in orange glass. I have an orange marker here, but it's a little beat up. And hell, you guys can't tell the colors. Oh, here's two. Here we go. Let's see if one of these is nice. This problem is about an orange party bulb. That's not coming out very great on your image there. All right, this is a little better. Let's try this one. So I'll draw a picture of a light bulb. And we'll have some photons of light coming off of it. And when we read the givens in just a moment, you'll wonder how I know it's orange. You might wonder. I know my wavelengths of light so well, and I hope eventually you will too, that I am well aware that in the visible continuous spectrum, I want to show you a better picture of the visible continuous. I hate how it just goes away when you. There should be like a presenter view for online where I can see the slide numbers and stuff. Visible continuous spectrum, that's 63. We should remember that number. And we should also remember 75. How could we forget 75? Okay. You guys will notice that they're going to give us a wavelength in this problem of 600 nanometers. And you can tell that 600 nanometers, it's pretty damn orange. You know what's interesting? Color is a psychological effect of wavelength. And our perception of orange is actually a very narrow range of wavelengths. Whereas there's a huge range of wavelengths that we call red. Like, I think most people would call this red and this red and this red and this red. All of that's red. But orange is a pretty psychologically narrow range. For us, the perception of orange is from like maybe 590 nanometers up to 610, pretty narrow band. And so in that regard, this problem is sort of about, well, it never does what I want it to do. Home Depot party light. Yeah. So you can get some fun party lights. Make your video game den or your music studio kind of cool. I don't know what they call them. I bought one the other day, an orange light bulb. It was nice. Okay, let's let you. Yeah, here we go. Here's like a party light bulb, something like this. Okay. All right, go ahead. Read us the problem, buddy.
All right. So, how many photons? Suppose that all the energy.
Sorry. Well, one last thing. This is 57, right?
Yes.
Okay. I just didn't want that to be confused.
All right. Suppose that all the energy from a 100-watt light bulb came in the form of photons with wavelength 600 Newton meters. No, I didn't say that right, did I?
It sounded like you did, but try it again.
It's not Newton meters.
Oh, nanometers.
Nanometers, okay.
Nano is billionth.
All right. No, in reality, light bulbs distribute energy over many wavelengths.
Let me explain that comment. There is a difference between a colored light bulb and a laser. I had my laser out the other day. We're going to need that for our demos.
The laser.
Laser. A laser is a monochrome. This isn't going to look as good over my camera as it does in my apartment. Let's see if I can laser you guys. Whoa. I don't think the CCD likes that very much. Shining a laser in your eyes. It's too bad you can't see, because I'm looking at the video on my screen and it's kind of a dull green point. But here, you guys know what a laser looks like. It's a brilliantly electric green color, right? And a laser is considered a monochromatic source of light. Monochromatic means it's just one wavelength. It's a really, really narrow range. And on this particular doodad, I wonder if I can get the camera. It loves to focus up close. So maybe I could actually use that to my advantage for once. I gotta get my face out of the picture. No, you're not gonna let me do that, are you? You stupid bastard. Ooh. You guys can see that they list the wavelength right there, 532 nanometers. So this green light, it's not just any old green, because any old green, there's a swath of wavelengths that we experience as green. From maybe 500 nanometers, which is kind of teal, all the way up to 550 nanometers, which is kind of a, what do you call this? Like a yellow green?
Puke.
Huh?
Puke green.
Chartreuse. How about that? Ooh, chartreuse. Okay, so from teal to chartreuse, but 532, that's a unique wavelength of green. In reality, those party bulbs, they're not actually laser bulbs. that would be way too cool, because they probably let out a range of wavelengths from 590 to 610. But a laser party bulb would be even nicer and probably more expensive. This problem is about a laser bulb because we're assuming all of the light coming out of it is just exactly 600 nanometers. Such a light bulb, if you could build it, would probably look fucking awesome. It tends to be that when you see a really pure color of a single wavelength, it just looks cool and electrified. Okay, go.
All right. So part A. Calculate the energy of a single photon with wavelength 600 nanometers.
Okay, this kind of sounds like a reprise of the last two problems we did. And it's not that hard, so I don't know. Who knows what to do here? Pick a number between 1 and 3.
Well, we could start with C. Number 1, because C is the constant, and we have the 600 nanometers,
Okay.
which we can find F.
Okay.
And then we can use formula 2, which, because H is given, and we'll solve for F.
Now, Joel just did a brilliant and totally unnecessary thing. Joel, I completely agree with you. We can go from wavelength to frequency, and then we can go for frequency to energy. But that's exactly what equation 3 does. If you plug C over wavelength into equation 2, equation 3 is what you just said already done.
Wait, yeah, because H and C are givens.
So we can go directly, and those were blue before, so that's partly my fault. I erased it and I forgot to put those back into blue. I know that those are constants, but that's not always obvious to you guys. So we can go directly from wavelength into energy. So let's do that. However, we should consider units as always. Up to now, Evelyn's been our unit master, but I'd like you guys to get knowledgeable about that too. Sarah, Jose, Will, what do you think we should do with our units here? Any thoughts? I guess I'm asking some different people in the class if this is cool, if this is okay. Not all at once now.
To meters.
I'm sorry, Jose?
Should we have to convert that?
Yes, and you said convert it to what?
To meters.
Exactly correct. Okay, I volunteer you for the job. So let's go. 600 nanometers. What units do I put in?
Okay. So nanometers on the bottom and meters on top.
Beautiful. And now you need a conversion factor, which I gave you in the previous problem if you look there quick.
So 1 would be on top and 10 to the negative 9th on the bottom.
Almost. I think you might have flipped those around. Because if you look at the equation, it's...
Oh, yeah, I did.
Right?
Mm-hmm. So 1 is on the bottom.
Yeah. If a professional scientist was doing this, they would certainly just simply write 10 to the minus 9. But you guys will remember in the previous problem that Laura made a mistake by plugging in 10 times 10 to the minus 9. I'm really worried that you guys are going to do that. So I'm going to make it really explicit and say 1 times 10 to the minus 9. Because I'm afraid that if I just write, sometimes scientists will suppress the 1 and just write 10 to the minus 9, but students can sometimes screw that up. Okay, Jose, I don't even think you need a calculator for this, bud. Because if you want, we can just leave that as 600, and then what would the answer be? 600 times 1 is 600.
Uh, 600 times 10 to the 9th.
Negative 9, right?
Yeah, negative 9.
Now, that's pretty awkward because I could make that 6 times 10 to the minus 7. But I like this because I can read 600 nanometers. Nicely done, Jose. Okay, now we are ready to plug this into our wavelength in equation 3. So the energy of the photon is, and let's use some purple units here, or let's use some orange units, I guess. 7 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8 meters per second divided by 600 nanometers. And I'd like to point out here that 10 to the minus 9 is the same thing as saying nano. That's what nano means. Nano means a billionth. Okay, punch them up. Anyone? Don't wait for me to do it. That's your job.
3.5 times 10 to the negative 19 joules.
What was the foreground digit?
3.
3 times 10 to the minus 19 joules. All right, I like it.
I got 3.5.
Oh, okay. Well, 3.5 works too.
It's a very simple number this time, Brittany.
I like it. I like simple. Works for me. All right, that takes care of part A. I'll leave that in the corner, and we'll go on to part B. I'm going to have to erase some of this, though. Okay. B.
How many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
We're looking for the photons each second. And each is a very loaded term here. What should the units of our final answer be?
Per second?
In a way, you're not wrong. You're kind of right, Laura. It should be the number of photons per second. In physics, I'm going to try to make this point because it's going to come up a few times in our class. And I can remember being really confused by this when I was a student. So I'm going to try to say it slow and careful. In physics, we make a differentiation between units which are hard physical concepts like meters and seconds in joules, and then a kind of loose concept like photons. Photons are not a loose concept. We know what a photon is. But a photon is like, it's not a physical unit as much as an idea. It's kind of like a doodad or a whatchamacallit or a thingamahini. And so for that reason, photons per second, photons are kind of like a dummy unit that are there to remind us what they are, but they're doodads per second. And in that sense, Laura was actually kind of correct. The units are per seconds. But this isn't frequency like electromagnetic wave hertz. It's a different type of frequency. As a great example, school is no longer in session at CCRI. Well, school is in session, but we no longer go to CCRI. But you guys can all remember going to CCRI and streaming through the front doors in the morning with lots of other people rushing to their classes. Imagine as an experiment, we were to stand at the doorway with a little clicker like they do at the nightclubs when they're counting the number of heads coming in the door. And imagine we clicked how many students were coming through the door per second. The units of that could be expressed in two ways. Students per second coming through the door. They could also be per seconds, as in people per second, or weirdos per second, or thingamahinis per second, something like that, right? So the units we're looking for are kind of like hertz, but they're not the frequency here. This is the cycles per second of an electromagnetic wave. We're not trying to find the cycles per second of an electromagnetic wave. We want to know the number of doodads that are streaming out of the bulb in all directions. And I think we're going to want to relate it to the energy, because the energy, 100 watts, sorry, that's not an energy, that's a power. The power of 100 watts is the same thing as 100 joules per second. So I already know the energy flow coming out of the bulb, but I want to somehow convert that into particle flow, if we consider the photons to be particles. I don't know if any of that made sense. What do you think we should do? I need a bold idea.
Formula 1.
Formula 1's not going to help us here. I'll give you a hint, Joel. We're not using any of these formulas here. We have to use our minds, or when our minds fail, a second option is to use, what's it called? I keep forgetting.
Calculator?
No, I mean, yeah, we're going to need that too, but there's this other technique. I'm trying to think of it. What's it called?
Dimensional analysis.
Ah, that's an idea. Yes. Okay, all right. Okay, Will, suppose we use dimensional analysis. Will, you're going to regret opening your big mouth now. Will, if I were to use dimensional analysis, how could I go from joules per second and convert it to photons per second? What units would I need to put there?
Say that again.
You suggested that we use dimensional analysis to get our answer. Our answer is how many photons per second are streaming through the bulb. I'm asking you, what units would I need to put in to convert joules per second into photons per second? I want to know what to put here. Put more simply, what do I do?
Joules on bottom.
Okay, that's a good start. And what would go on the top?
Seconds.
No, we want to keep the per second.
I'm trying to turn it into.
You're trying to make this look like this.
Photons.
Say that.
I don't know. Photons.
Photons. That's right. We need a conversion factor from joules to photons. Man, if only I knew how many photons there were per joule. Or I guess another way to say it was, if only I knew how many joules there were per photon, then I would be all set in this problem. If only I knew how many joules there were per photon.
Yeah, let's see.
I wonder where I'd find such a thing.
In that
It
little
must
box.
Be, it must be, yeah, right there, right? Because
Yeah.
isn't this the number of joules in one orange photon? This is
Gotcha.
actually like joules
Sure.
per photon. Right?
Yeah.
It's the number of joules per one orange photon. Okay, so Joel, since you're with me, what do I put in here?
My stupid big mouth.
Yep.
One on top,
Yep.
and then the box on the bottom.
Exactly. And what do we get there?
Um, 3.5 times 10 to the negative 17.
No, it's got to be, you're dividing by negative 19. The number's got to be huge.
Or is it minus 21?
It's got to be positive. Look, 2 minus negative 19 is positive.
It's minus 17.
No way.
Positive 2 minus. Oh,
2.8 to the 20 times 10 to the 20.
Let's just call it 3 times 10 to the 20. Units?
We'll have photons.
Not just photons, but
Per second.
photons per second. Wow. That's a big number. In 1 second, a 3 followed with 20 zeros worth of photons come out. Is there a name for such a word? Like, it's good to have this Wikipedia page. Names of big numbers. Let's see. 10 to the 20. Well, 10 to the 21 is a sextillion. 10 to the 18 is a quintillion. So that's 19, 20. That's 200 quintillion photons in 1 second. Holy smokes. Are you eating my noodles? Damn it. Wow. My leftover noodles are being eaten as I speak, and I'm powerless to stop it. Okay. There's going to be some hell to raise during break here. Okay, so what's part C, ask us?
Let's see. Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
Another way to state this question, C, is, here's a better way to state that question. Why can't I see a single photon? What do you guys think the answer to that is, based on your answer to part A and based on your answer to part B?
Our eyes aren't capable of distinguishing that something that small. It's such a big.
Okay, well, hold on. Let's deal with that suggestion. Small. I agree with you, Shay. I agree that 600 nanometers is pretty effing small. What do you think the smallest thing a person can see is? A person can see a millimeter, right?
Yeah.
Can you see a 1/10 of a millimeter?
Yeah.
If you had really good eyesight.
Yeah.
Maybe. Can you see 100th of a millimeter?
No.
I could.
No. I mean, look, where's my bloody ruler here, right? This is, we're seeing it through the camera eye, but
You're still on sharing.
okay, stop share for a second. You know, those little ticks are millimeters. Maybe you could see a tenth of it, but 100th. Now a micron is a thousandth of a millimeter. If you could take 1 millimeter and break it into 1,000 parts, can you see a micron? Whew.
No way.
Hell effing no. Can you see a nanometer, which is a millionth of a millimeter?
No.
And so I agree with you, Shay, that 600 nanometers is pretty small. There's just one problem with that argument. All orange light has a wavelength of 600 nanometers. So if 600 nanometer light was too small to see, then you wouldn't be able to see the color orange. Shit, that can't be right. Our eyes are designed to detect photons of 600 nanometers.
No, but we can't distinguish between them.
What do you mean distinguish
The
between
little
them?
packets, all the little packets are smushed together, flying around. You
What, like,
can't.
because there's too many of them?
Yes.
Yeah.
Okay, we've ruled out small. Now let's try the next one. There's too many of them. This is also a mistake. It's an error in logic. You're assuming that if there's too many of a thing, that is reason to not be able to see a thing. But I could think of a million cool examples of how that's wrong. Let's go to the beach and let's pick up grains of sand. Now, I think anyone would agree with me that there's too many grains of sand on a beach to count. And yet, if you pick up in your hands these too many grains, you can see them. Just because there's too many of a thing does not mean you can't see an individual thing. I can pick up a handful of sand, and even though there's millions and billions of grains of sand, I can still see individual grains. There's too many stars in the sky, but I can see individual stars. There's too many leaves on a tree, but I can see an individual leaf. That doesn't make sense to me. It can't be that it's too small, or I wouldn't see the color orange. It can't be that there's too many, because just because there's a lot of something doesn't mean I can't see one of them.
They're glued together.
They are not glued together.
It's the speed at which it travels to your eyeball.
Let's try that one. They're too fast.
Leave it up to the Navy guy to answer the question.
Except it's still not right. Isn't it true that all light travels at 3 times 10 to the 8 meters per second?
Yeah.
Well, can you see light? Yes or no?
Yeah.
So if light was too fast to see, you wouldn't see any fucking light. That's also clearly incorrect. All light travels at the same speed.
But do we actually see light? We see the effects of it.
Okay, yeah, this is getting
right.
Okay, so let's talk about it then.
Oh.
Wait a minute. So let's look at a diagram of the human eye. Well, how does this work? When we detect light,
There are cones and rods in your eye.
right?
Reflection of the light.
Right. So it's what happens is the photons come in through your pupil. Let's see if I can annotate here with some orange. So here's some orange photons, and they come in through your pupil, and they're focused by a lens, but they propagate through the vitreous humor, this goose sac. But where they are converted into a signal is here, at the retina. The retina captures the photons, and the photons are then converted into an electrical signal, so you can say, orange sherbet. That sounds tasty. Now, why can't my eye detect one single photon? It can't be that it's too fast, because it's traveling fast and I still am detecting it with my eye. It can't be that there's too many, because even though there's too many, I can still usually see an individual object. It can't be that it's too small, because my eye is designed to see this 600 nanometer light. It must then have something to do with the answer to A and B. Let's try a different question. Suppose I invented the world's smallest light bulb, a quantum party light. And this quantum party light was a little microscopic atomic-sized bulb, and it could only emit 1 photon per second. Can you tell me what the wattage of that bulb would be? You should be able to. If it only emitted one 600 nanometer photon in each second, it's a little quantum party bulb. In a way, atoms are actually kind of like little quantum party bulbs. But we're assuming this is a slow party bulb that only emits one photon per second. What would the wattage of that bulb be? How many joules per second would it pump out? Look at the board.
The 3.5 times 10 to the negative 19?
Right, but in this case, it would be watts. It would be 3.5 times 10 to the minus 19 watts. Now let's think about some bulbs in our everyday life. Hold on a second. I don't know. I was hoping I had some incandescent bulbs. Here's
No cheating, Will.
This actually is an orange light bulb. I actually have a party bulb right here. How many watts is this? Oh, these are
60.
LED bulbs. Well, it's designed to be for incandescent. Today you'll learn that if you use LEDs, they can use much less power.
Yeah.
That's because they put it all into the visible domain. This is only like a 5-watt bulb technically, which is fucking wild to me.
Ooh.
This one is only 4 watts. Well, LEDs have changed our wattage and our concept of that. I don't know why I'm getting Reddit tags to my thing here, but I want to.
So that 3.5 times 10 to the negative 19 watts, would the naked eye even pick that up, even in a completely black room?
That's my fucking point. You're getting right to my point, Joel, is how dim a wattage do you think the human eye can see? Like, I think I can see a 1 watt bulb. Oh, hello, youngster. A 1 watt bulb is a 1 watt bulb is like a Christmas light, right?
Yeah.
And like a Christmas light bulb, maybe 1 watt. Do you think you can see half a watt?
Yeah.
Well, she's a real cutie. What's her name?
Her name's Cosette.
Hey, Cosette, how's it going?
Good.
Are you joining the science class today to learn about light bulbs? Cool.
Mm.
All right, well, we're gonna have some fun demos for you today, okay? I think I could see a half a watt or maybe a quarter of a watt or a tenth of a watt. I read once on the internet that the human eye in a dark adapted room can see down to a millionth of a watt. And that's because that's comparable to the luminosities of stars. But Joel, do you think we could see a 10 to the minus 19 watt bulb?
No.
No way. So what's the
Well, I might be able to see it, but I wouldn't register it.
That's just it. You wouldn't detect it. It would be like a mosquito that lands on your hand. Mosquitoes can land on your hand so delicately that the sensors on your skin don't register it. There's probably a minimum threshold to trigger the cells in your retina. So what's the real reason why we can't see a single photon?
Too dim.
Kind of. Too dim is brightness, but a simpler way to put it is there's not enough energy in a single. It's about energy, guys. It's about energy. There's not.
We said that, Brendan.
Yeah, like
You
10
just
minutes
did.
ago.
You just didn't translate it into the word you were looking for.
Oh, you mean went from dim to energy? Hold on. I can tell you why that's okay. No, I've thought this through.
We're totally joking with you. We suck.
No. You guys opened up the
Well,
Pandora.
we were on the right track, but we weren't putting it into the correct terminology.
Yeah.
Right, but I can only torture you for so long, but let me follow my argument. Dim is the equivalent of brightness. Brightness,
Right.
as you'll learn today, is watts per meter squared, and watts is joules per second. When you're talking about a stream of photons, you can talk about joules per second. But when you're talking about a single photon, you can only talk about the energy because it's one photon. Now, I wasn't going to get into the semantics until you guys called me my hand on it. But I didn't bother explaining to you. What I was really thinking in my head when you said dim is, no, it can't be dim because dim requires a flow of photons per second, but we're only talking about 1 second. And then I thought, TMI, no one wants to hear that. Let's just say energy. Do you see my logic? But dim is related to energy because if there were many photons, we could say dim. But when you're talking about a single photon, it just has one packet of energy. So a single photon does not contain enough energy. Let's write that down.
Like hair on the head. If you have a single strand of hair, some people may or may not see it.
Exactly.
We have a bunch.
Are we speaking? A single photon doesn't have enough energy for the eye to register it. So what's so cool about that problem is our tendency is to go towards things that we understand, size, number, speed, but it's about a more abstract concept. It's about the energy, which is a lovely, lovely problem. Okay, let's talk about our plan here. We'll take a little break for 10 minutes before lecture starts. I need to put up your lab today. We've now completed our homework. I also kind of need to set up some lab demos for you guys, which I foolishly did not do, but they're all sitting around here, so it should be okay. At the end of class today, we'll talk about our exam. And yeah, that's all I can think to say right now. We have to talk about the exam before class ends. So you guys want to take a little 5-10 minute break? Just drink some iced tea or something, chill out for a sec. Okay.
Yeah.
Let's take a little pause, and in 5 or 10 minutes, like 5 past, we'll get back into it. Okay, everyone. I had a couple noodles, now I'm back. I salvaged what I could of my leftovers. We're going to talk about light today. It should be good. I'm going to skip the intro, and I'm just going to get right into business here. Let's think. At the end of our last class, we learned a little bit about atoms, and we learned about wavelength, frequency, and energy. And you guys had some nice examples of that in your homework. I want to start off the day by introducing a really important concept called the inverse square law. And I want to talk to you about power and energy and kind of have fun with it here. So there are 2 different ways we can talk about light. The light bulb problem illustrates it perfectly. I can talk about a single photon, that is a particle of light, like the ones that we just discussed. But when I talk about an entire light bulb, you guys have started to realize now that that's not just emitting a single photon, it's emitting bazillions and what was the word again? Quintillions of photons? At one moment, a light bulb can be pumping out 10 to the power of 20 photons in a single second. So that's a mind-boggling number of photons. When we deal with the macroscopic worlds, the world of everyday objects, it's so much larger than individual atoms that we almost need a different approach. And this is a big theme in physics. You can tackle things from a macro perspective, a large-scale, human-sized perspective, or you can think about things from the microscopic perspective, where the world of atoms and quantum mechanics dominates. And then at some point, you have to figure out how to thread those 2 things together and have them meet in the middle so you can simultaneously see the big picture and the small picture. It almost sounds like politics in a way. So we're going to focus on the macroscopic for a minute, and we're just going to meditate on a light bulb emitting a ton of light. Let's look at a couple of slides from my slideshow for help here. Suppose you asked yourself an awkward question. Suppose you said, I want to attempt to measure the energy of a light bulb. One way you could go about this, function F527. Sorry, I got to say it out loud. So I'm recording right now, right? I remembered to do that. Does it say recording up there? Yeah, okay, good. I grabbed myself a light bulb. It could be a fancy LED light bulb or an old-fashioned incandescent light bulb. And believe it or not, there are tools for measuring the energy that is emitted from a light bulb. And the tool is called an integrating sphere. And the way an integrating sphere works is they have a sort of Edison socket in the middle here. You plug in your light bulb. This is all a photosensitive collector that can measure the intensity of light, kind of like an old-fashioned photographer's light meter. You close up the sphere so that it's only catching the photons in all directions. And then you use your computer terminal to read out the energy coming out of the bulb. But of course, if you ever tried to do this, you'll quickly realize that asking the question, how much energy comes out of a bulb, is kind of the wrong question. Because you'd have to sit there and turn a fresh bulb on, and you'd have to wait for it to burn out, which could take months, or in the case of an LED bulb, maybe even years. Because photons are constantly streaming out of the bulb, you start to realize that the question shouldn't be how much energy, but how much energy is coming out in some interval of time, like a day or an hour, or if we're going to use MKS units, a second. What you are doing then is you are not talking about energy anymore. You're talking about power or luminosity, which are kind of the same thing. In a general physics sense, power, as I mentioned in office hours, sorry, that's the bad one. Power is defined as energy per unit time. And the units of power are the watt. 1 watt is equivalent to 1 joule per second. As I mentioned before, anything that uses energy can have a power. So powers can be expressed in all sorts of different ways. For instance, the power requirements of a daily human are 2,500 calories per day, which is equivalent to roughly how many watts?
About 120.
Right. In your books, they have another interesting tidbit. The United States of America, in 1 year, uses 10 to the power of 20 joules per year. And that's a power because it's telling you an energy per unit time. Hair dryers can have a wattage. Amplifiers can have a wattage. Humans can have a wattage. Light bulbs can have a wattage. Ooh, but when we talk about light, power gets a unique name. We don't call it power anymore. We tend to call it the luminosity. Luminosity is the exact same thing as power. It's just, when we talk about light, we tend to say luminosity rather than power. It's the power of light. And luminosity is measured in watts, just like power is. A light bulb could have 100 watts of power or emit 100 watts of power. Or it could be an LED light bulb that has 5 watts. The luminosity of the sun is also a constant. And as we'll learn, the sun's total light output in all directions has been remarkably steady for billions of years. It has a value of 4 times 10 to the 26 watts. That's a crazy ass amount of power. It's hard to, underemphasize or hard to overemphasize just how much that is. Man, this gives me a nutty idea. Class, what if we could build an integrating sphere that was so big it could cover the entire sun, a giant solar panel bag, and then we could harvest all of the photons from the sun, and then we would be like a sort of star tick that's sucking the energy of our own star and using it for our nefarious purposes. The science fiction writers have a name for this after Freeman Dyson, who died this year. It's called a Dyson sphere. And he imagines that a futuristic civilization of humans, or maybe even some advanced aliens, could construct a massive solar panel that surrounds their star and gobbles up all of the photons. Cool idea, bro. Now, guys, here's a thought question for you. What if I could build a Dyson sphere? And what if I could collect 1 second of sunlight? Can you guys tell me how much energy I would have? So I get 1 second of total sunlight. In other words, in 1 second, the sun will give off an energy of, take it away, class. Really? No? Nothing?
4 times 10 to the 26 joules per second.
Joules per second is an energy flow. I'm asking about an energy. Try again.
4 times.
Joules.
Yeah, watt.
4 times 10 to the 26 joules. Is that a lot of energy?
Nah.
How does it compare to the energy output of the United States, or the energy consumption of the United States in 1 year? Here's a question. If I could collect 1 second of sunlight, just for 1 second, I grabbed every single photon that came out of the sun, how long could I power the United States energy needs?
More than 4 years?
Say that?
What is it, more than 4 years? Because it's 4 times.
It's a little bit more than
4
4
times 10 to the 20, or 10 to the 6?
4, yeah, so that's joules divided by 1 times 10 to the 20 joules per year. Joules cancel and leave you with 4 times 10 to the 6 years, right?
Mm-hmm.
What does that mean?
So 1 second of the sun's energy could power the U.S. for 4 billion years.
Isn't that insane? Isn't that insane? If you could just grab 1 second of total sunlight, 4 million years. And let's just look at United. There's a beautiful.
Is it 4 million or 4 billion?
10 to the 6 is million.
Oh, yeah.
Right?
But why would it matter if it was million or billion?
Well, because
Like,
3 zeros matters.
Well, yeah, but the number's just so huge that we can't even really comprehend that.
Yeah, I mean, well, it's easier to comprehend a million years than a billion years. But yeah, I think the point is that's stupid, right? That's
right.
That's stupid. The entire U.S., all of the light bulbs and the street lamps and the toasters and blenders and the video games and the electronically controlled devices, everything you could think of, 4 million years of free juice. No more would we be servants to National Grid. Oh my gosh. That reminds me.
Yay!
Someone remind me to pay my internet bill during tea break, or they will end this lecture prematurely. Cox, don't give up on me just yet. Actually, I'm kind of terrified of that. They sent me a nasty text this morning. I got to do that at tea break, okay? And if the lecture spontaneously ends, it's because Cox came to get me. Okay.
You got a week.
Yeah. Hey, why haven't we done that? Why haven't we built ourselves this Dyson sphere?
Does it have to do with gravity?
Well, no, it has to do with practical things like.
Too friggin' hot.
Well, you could put it sufficiently far away so it's not too hot at Earth distance. You could just make a really, really big sphere. I guess we don't have enough materials on Earth to do that probably, but we could mine some asteroids. If you made it sufficiently thin, I guess we're just not there technologically. We don't get to capture all of those photons because the luminosity is the light output in all directions. Most of the photons emitted by the sun just disappear into space so that aliens can see our sun as a little star twinkling in their sky. We're not capturing all of them. We're only sorry, let me clear this. Let me get a straight line.
The aliens are stealing our sun.
They are stealing our, in a way, aliens are stealing our sunlight. And when we look at the stars, we're stealing the alien sunlight. So it's a big game of wasted photons. We only capture a small cone of light. Whatever cone actually splashes down here on Earth, I was trying to get a cone. Ooh, that's kind of cool. Ooh, that's not as cool as I thought it was going to be. We only get a small splash of that light that actually makes it over here to Earth, right? Like it's some kind of angle or some kind of cone that actually makes it to Earth. The other photons are all just passing by us or passing in the wrong direction. This is a nice illustration of a second concept that I need to introduce to you today. It's called the brightness. You don't detect luminosity because luminosity is the light output of a bulb in all directions. Your eyeball sits at some distance away, and when I say eyeball, I really mean detector. Your detector could be a solar panel, it could be a camera lens or a telescope, or it could be the pupil of your eye. And you're gathering some fraction of that light. That concept is the brightness. So let's differentiate between luminosity versus brightness real quick. Luminosity, L, is the light output in all directions. And because of this, it's usually a fixed number for some object. The luminosity of the sun is fixed. A 100-watt light bulb is a 100-watt light bulb whether you're close to it or far away. But you detect brightness. The brightness B is defined as the luminosity per unit area that the light is being splashed over. So your cartoon picture is you've got some panel and your light source is emitting light across that panel, right? And your area is here. And the bulb's luminosity is here. There's light going in all directions, but you're capturing a fraction of that. Now, in this case, it can be good to remember that if your light source is a star, and the starlight is being spread over some sphere of radius r, that the surface area of a sphere is a known quantity from geometry. The surface area of a sphere is 4 pi r squared. Because my picture is kind of crappy, let's look at my screen picture for just a hot moment here. take a look at this picture, because this picture is excellent. Imagine the luminosity of the sun traveling through space. And remember, the luminosity of the sun is 4 times 10 to the 26 watts. Presuming that there are no planets and no dust in the way, at each successive growing of the radius, the 4 times 10 to the 26 watts is being splashed over a bigger and a bigger and a bigger sphere. And what that means is the brightness that you get at any one of these panels is getting weaker and weaker as you go more distant in space, because here, this little cone of light is being spread over an area 4 times as big, and now that cone of light is being spread out over an area 9 times as big. What a cool way to do it is to take the luminosity of the star and divide it by the surface area of the entire sphere. So you're basically dividing it into a whole number of panels like this. And when you plug the surface area of a sphere into the brightness formula, you get a legendary and very useful formula called, and I want to draw my picture a little better for your books here. So here's the sphere. It has a radius r, and we're considering how much light is coming through one solar panel. That's the brightness. It's known as the inverse square law for light. Brightness equals luminosity over 4 pi r squared. That's one version. If you, instead of calling the radius of the sphere r, call it d, as in that's how far away from the star you are, you could also write it in a different way. Brightness is luminosity over 4 pi d squared. In fact, both of these equations are the same equation, but because there's a couple of different ways in which you can use it, it's a very useful formula. I'm having you write it 2 different ways to let you know that sometimes you can plug in the radius of a star, sometimes you can plug in the distance to the star. This isn't going to make a lot of sense until, yeah.
Those aren't the same, because r squared would equal, r squared doesn't equal d squared, because the diameter is twice as long.
No. Okay.
Or am I thinking about that backwards?
This, when you are new to algebra, unfortunately,
I didn't see the little d. Okay.
Yeah, d is not diameter here. D is also distance.
Okay.
What's going on here is worth talking about. Most of you have only recently taken an algebra class, or conversely have taken it so long ago that we forget a lot of our maths. And when you're just learning math, you tend to get a little obsessed about what each of the letters means. R has to stand for radius. D has to stand for distance. But as you get more experienced, you realize that this quantity is just a quantity of unit length, some kind of length. And in different contexts, you might change the variable to represent something different. What I'm saying is D is not, I think you already answered your own question. D is not diameter.
Yeah, I did.
All right. Let's try a little sample problem, okay? This, honestly, the talking doesn't help. The doing of a problem is what helps. That's why we do sample problems. Let's imagine I have an astronaut on a spacewalk. Let's just call up a picture here. Now, the reason I'm choosing an astronaut on a spacewalk is I don't want to get muddled up with the atmosphere of Earth. The atmosphere of Earth actually absorbs some of the sunlight. But I want to be at Earth's distance. So let's say I've got an astronaut. Now, this is not a solar panel here, but let's imagine that in his hands, he was holding some kind of a solar panel. And the solar panel was 1 meter squared. So it was 1 meter in length, and it was 1 meter in height. So he's holding up a solar panel, and he's gathering sunlight. I want us to calculate what would the brightness of the sun be on that solar panel as seen from Earth. So let's set up that sample problem. Find the brightness of the sun at Earth's distance. And here, Earth's distance is obviously 1 AU. Now, class, what do you suppose the units of brightness should be in the MKS system? Really? I thought this would be an easy one.
I'm gonna say seconds, but I don't know.
You just got to look at the equation to figure out what the units are. What are the units of luminosity? You better look in your notes. You're all forgetting stuff.
Watts.
Watts. What are the units of radius or distance?
AU.
They could be, but that's not MKS. Watts are MKS.
Or meters.
So what would your units of brightness be then?
Wait, what? Say that again.
What are your units then of brightness?
Watts per meter squared.
Thank you.
I'm smart.
So if I want to calculate the brightness as the luminosity of the sun divided by 4 pi d squared, hey guys, can you give me 1 second? Auto repair, 1 sec. Hello? Hi. How you doing, Sam? Ah, you are a lifesaver. My class ends around 4 today. Can I come by between 4 and 5? Ah, you are a wizard, sir. I appreciate it very much. Okay, all right, bye. Hey, I'm sorry I had to take that, guys, but you know, like when your car is in the shop and they've got to call you to say, are you okay with being destroyed financially for the rest of your life while we make this repair? I wanted to make sure that I could give him the green light to go ahead with that so that my car would be ready. So I apologize for interrupting class, but you know how it goes when you've got the car repair stuff. It kind of takes over your life a little bit. The good news is for once I got out pretty unscathed, so I'm happy. Okay, if we're going to put in the luminosity of the sun, we know the luminosity of the sun is 4 times 10 to the 26 watts. But we can't put in 1 AU, right? What are we going to put in instead?
1 times 10 to the 9th.
That's 1 billion. 1 AU is more than that in meters. Do you guys remember how many meters an AU is?
It's 1 times 10 to the 6 kilometers.
It's 150 million kilometers, right?
So in meters, it would be 150 times 10 to the 9th.
Excellent. I wanted to see if you guys could.
Isn't that what I said?
You said 1 times 10 to the 9th, I think.
Oh, okay.
I think you knew what you were talking about. I think the words just got mangled on the way out of your mouth. That happens.
I'm still having trouble with numbers.
My purpose in asking you that is I already know that an AU is 150 billion meters. If you guys know that too, then we can just proceed from there. If you did not know that, we were going to have to do the dimensional analysis. But at least one of you knew that, so I'm going to proceed from there. So I've got 4 times 10 to the 26 watts. I'm going to divide by 4, divide by pi, and divide by 150 billion meters squared. Can you guys do that for me? This is not as easy as it looks, so I want you to punch this in. And show me your calculators. You know what the other class has started doing? And I actually think it's really cool, and I'd like you guys to start doing it. In the other class, once people get the answer, they hold their calculator up to their camera like I'm doing now. You got it, Laura. What's so great about that is I can check on all of you and make sure you're all getting it. And if you're not, I can give you the personal attention you need. So I'm not saying you have to, but I think we should. Like Laura just flashed me her calculator and I could see that it was correct. And if it's not, then you can try it again. That's good, Joel. You got it.
Could you move just like to the left?
Sorry. Yep, you got it, Will. You got it. Evelyn, it doesn't, hold on, hold it up, keep it there. Evelyn, something went wrong, and Jose, you both had the same issue. Can I tell you what your issues are? You guys need to divide by 4, divide by pi, and then divide by 150 exp9 squared equals. I think you're forgetting.
That's what I did, but I don't know what.
Evelyn, could you just punch it one more time for me? I think you hit a funky button. And Jose, can you punch it one more time too? Jose, your problem, I know what your problem is right away. You hit times here, but I need you to hit divide. So 4 divide by pi.
Divided by pi.
Divide by that squared, and don't forget to hit equals after you square it. So try it one more time.
Is that right?
Yeah, you got it now. Will, how about you, dude? How you doing? Did you already show it to me and I forgot? Oh yeah, you got it. Okay. Jose and Shay? Shay, have you got the Casio yet, or are you still rocking that phone thing? Nope, didn't come out right, Jose. Jose, I want you to follow along with me, okay? I'm not sure what you did this time, but just follow me because it's pretty easy instructions, okay?
Yeah, I need a refresher. I screwed something up.
That's all right. All right, so let's just do 4 exp26.
Yep.
Now, divide by 4.
Divided by 4.
Divide by pi. Divide by 150. exp9.
exp9.
Hit the square.
Square?
Yeah, you have to square the distance, right? You see that?
Okay.
Now that's what you're forgetting to do, forgetting to square it. And then hit equals.
Oh, I put, because we got used to hitting the shift.
Oh,
because
so
we were using the square root for a long time. So I kind of got used to hitting the shift before hitting the button. So that's what I did wrong.
I've seen that before too, right? Yeah. Try to remember that the shift gets you the orange menu, which is the square root. But we needed the main key, the square.
Yeah.
Okay, that's cool.
So that's what I did.
All right, so we know now. And Shay, you got it too?
Yeah, all set.
All right, so you got, what's our final answer then?
1414.710.
Whoa. Let's
bring
it back down to outer space here for a second. How about 1400?
Yep.
right? Because the extra numbers don't really mean much. And that's watts per meter squared, right?
Yeah.
A square meter is pretty big. Actually, ironically, the surface area of this dry erase board, you'll notice, is pretty close to a square meter, right? This dry erase board is pretty darned close to 1 square meter. So a square meter, like this is bigger than a pizza box. You guys aren't here in my room, but you can see that it's almost as tall as my bookshelf. And, well, geez, it's kind of like almost like a refrigerator box or something, you know? A square meter is pretty big sized. And you'll see that I could power, if I had 100-watt light bulbs, I could power 14 of them with that solar panel. Believe it or not, if solar panels were 100% efficient, you can get a pretty good amount of juice from them. Although I did not ask this problem as a homework assignment, one of the funner problems in the back of the book in this chapter asks you to calculate how big a surface area you would need to power the United States energy needs if you had a perfectly efficient solar panel. And it turns out that if you're just willing to sacrifice a state like Connecticut or maybe Delaware or something and just pave it with solar panels, you could probably get free juice for life for the rest of the country. So Connecticut, I could be worth it, you know. 92 exits of pure hell.
Well, plus half of Connecticut are basically consider themselves New Yorkers. They like all the New York teams, so we can get rid of that.
One thing's for sure, we can't give up Rhode Island. It's too vital. Okay, so this is an example of how we do brightness. I need to say something here because it's going to come up during the test, and I know you guys are going to get confused on it. So I've got to try to rectify this. We just calculated a famous number in physics and engineering. It's known as the solar irradiance. The solar irradiance tells you how much energy the sun is delivering to Earth at the top of Earth's atmosphere. You want to take a guess how much it gets reduced when it gets down to the ground? So this is at the top of the atmosphere. Guess what it turns to when how much the atmosphere absorbs? So this is at the top of the atmosphere. By the time you get down to ground, it's been reduced to 400 watts per square meter. That's pretty wild because it means you're losing about 2/3 of the energy of the sun just getting absorbed in our own atmosphere. Solar panels in space go a lot farther than solar panels on the ground. Now,
that's not bad though.
It's still a decent amount of juice because this is a square meter, and you could, if you cover your house with them, you probably have enough wattage if it stays sunny to power most of your energy needs.
Can you
now listen?
Can you give the definition of solar irradiance again?
Yeah, it's the brightness at the top of the atmosphere. It's the brightness it's the brightness at Earth's distance. But that's not the thing I told you were going to get confused about. That was a bonus thing. I'm kind of jumping around. Here's the thing that you need to pay attention to, okay? I need to erase this for a second. Can I erase this? There are 2 uses of the inverse square law. I'm going to make this very, very explicit. 2 uses for the inverse square law. And you guys just did one of them. One of them is when you have to figure out the brightness of a star on your sky. And in a way, you guys just did that variation, the brightness of a star on your sky. And what we did is we used the brightness is the luminosity of the star divided by 4 pi d squared, where d is the distance to the star. For instance, we just got 1 astronomical unit as our distance. Normally, when you calculate the brightnesses of stars, they're much, much dimmer than 1400 watts per square meter. A typical stellar brightness could be 10 to the minus 8 watts per square meter. That's use 1. Use 2, which you haven't thought about yet, is you can calculate the brightness at the surface of a star. And I just happen to have a slide on that, so I'd like to share it. So here's calculating brightness at the distance from a star. You're here, the star is there, and you're calculating its brightness. This is the other one, where you want to basically take 1 square meter at the surface of a star and ask how much light is shining through it. In that case, you don't want to use the distance to a star, you want to use the radius of a star. So this is calculating the brightness at the surface of a star. And in that case, you want to use the luminosity of the star divided by 4 pi r squared. This is the radius of the star. Now, I've been doing this so long that I forgot this was an issue. But over the years, I noticed one place where students kept getting screwed up is in the same set of problems. I'll sometimes ask them, find the brightness of the star in your sky, and then find the brightness at the surface of the star. And I realized that students were getting hideously confused that they had to use the same formula by plugging in 2 different numbers. And it made sense that you were confused. And this is me attempting to deconfuse you beforehand. So for instance, in our last problem for the sun, we got 1400 watts per square meter. But if we had done it at the surface of the sun, what we would have done instead is we would have calculated the brightness is the luminosity of the sun, 4 times 10 to the 26 watts, divided by 4 times pi times the radius of the sun, 7 times 10 to the 8 meters squared. And I think you get something like 69 million watts per square meter if you do that. Or, I'm sorry, 65. 65 million, I think. You'll notice that the numbers are wildly different. 1 is a huge number because that's how much light is coming out of a square meter at the surface of your star. This is how much you get by the time you're 1 astronomical unit away. Now, I don't know if that made sense to you guys or not, because it makes sense to me. And once something makes sense to you, it's hard to unsee the sense in it. So you guys could give me some feedback here. Did that make sense to you, or do you need me to explain that more? Because you will have to do this on a test, and I'm trying to help.
Yeah, it makes sense.
Okay.
That is a good thing to know, because I would have totally screwed that up.
Yeah, I think so. For instance, on the test, can I give you an example of how this would flow? On the test, I might pick my favorite star, or one of my favorite stars. So let's say I pick the star Vega, which is a possibility. I might pick Betelgeuse, I might pick Sirius. I can go on the internet and look up the star Vega, and I can give you 3 numbers. I can give you its luminosity. Its luminosity is 40 times that of the sun. I can also give you its radius, which is about 2.5 times the radius of the sun. And I can give you its distance of 25 light years. I could then ask you to calculate the brightness of Vega on my sky, and then calculate the brightness of Vega at its surface. Do you guys think you'd be cool with that, or would that be a challenge?
It'd definitely be a challenge, but I think they can give it a shot.
It will cost us class time that I need, but I could do that as a sample problem right now if you wanted to. Or maybe you're not sure if you should do it or not. We're definitely going to do, okay, you know how we're supposed to have office hours every day? If I haven't mentioned this now, there's a plan for the exam. The exam, we're going to I haven't figured out how I'm going to deliver it to you. It's going to be multiple choice, and I think I can give you a multiple choice exam through Blackboard, but I've never set one up yet. So that's my job this weekend, is to kind of figure out how to do that. But presumably you'll be able to log in. And I think in other classes that are asynchronous, they just say, do the exam at some point and you're on your own. You got 3 hours to do it. But when I give an exam in person, I really like being there so I can be a part of the struggle and I can be available for hints and suggestions. I treat a test like a full contact sport. If you're getting totally stumped on a question, I'm not against coming over and giving you a little passive aggressive hint or making fun of you for a minute and pushing you in the right direction. Because I think sometimes, like with a little push, you know, sometimes you have to jump start a car. I think if I can just give you guys a little push, then you can do the rest on your own. And I think it's so silly to miss all those points because you couldn't get a little hint. However, in that same spirit, during the office hour session, we're not going to work on homework. What we're going to do is I'm going to give you sample problems like the ones we were just doing, and I'm going to see if you can solve them on your own. I'll make the sample problems almost exactly the same as the test questions. And then we can talk through them together before you have to go into war, right? So it's kind of like training before the battle. We'll simulate the battle. And I'll change the numbers, but I'll basically give you the same questions, and I'll even show you how to do them. I'll make you try it, but then I'll show you how to do it. And then that will kind of prime the pump a bit. Don't you think that would be a useful use of our office hour time? Now, Shay and Laura have been through my other course. So what do you think, Shay and Laura? Did those sessions help, yes or no?
Oh yeah, badass, big time.
Definitely.
Okay.
Yeah.
So that will be good. And that way it won't be as scary as going in cold, okay? So we're going to be able to do some of these problems during the office hours. I just don't know if it's worth doing it now, or we kind of just did one, but I'm worried that it wasn't enough. Yeah, okay, Alba. Alba's saying, can you give us sample problems of what the test would be like? Okay, so Alba's basically saying, can we try that? Let's just do it real fast, okay? Here we go. You've got the formulas. Does everyone have this down? All right, here we go.
So basically, Brendan, it's like driving down the street and seeing a street sign, and from like 100 meters away, it's pretty small, and then once we're right up on it, it's huge.
Right, but that analogy is about angular size. Angular size and brightness are somewhat related, but they're separate issues.
Well, yeah.
The angular size could come up too. Obviously, I don't have enough time to give you an example yet of every type of question, although I will try during office hours. But here's an example of how we could use two verses in the exam. Let's say there's a famous star and the star's name is Vega. Vega's luminosity is 40 times the luminosity of the sun. Its distance is 25 light years away, and it has a radius of 2.5 times the radius of the sun. Now, I will give you the luminosity of the sun, the radius of the sun, and the conversion from light years. The luminosity of the sun is 4 times 10 to the 26 watts. The radius of the sun is 7 times 10 to the 8 meters. And 1 light year is obviously 9.5 times 10 to the 15 meters. Actually, usually I give it to you in kilometers, and then you've got to convert it to meters. Okay, here are the two questions. Find the brightness of the star at the surface of the star. 2, find the brightness of the star on our sky. Okay, let's pretend this is the test. What the shit are you going to do? You're sweating. You're feeling the hurt. What are you going to do? Question 1, how do I do it?
So
let's first choose a formula, and then let's worry about units. What's the formula?
B
L.
equals L over 4 pi r squared.
Excellent. That's the correct version of the inverse square law. Now let's worry about the units. What do I want my luminosity to be in?
Watts.
So how do I do that?
So for the Star Vega, you're saying it's 40 times brighter than
The sun.
the sun. Okay, so it'd be 40 times 4 times 10 to the 26 watts.
Excellent. And that would be what? 4 times 4 is 8. I'm sorry. 4 times 4 is 16, right?
160 times 10 to the 26 watts.
Okay. So now, what about the radius? The radius is 2.5 times the sun.
2.5 times 7 times 10 to the 8th, which is 15 times, meters. 15 times 10 to the 8th.
Nice.
Meters.
I like your style there too. That's fast. So now we plug them in. 160 times 10 to the 26 watts over 4 over pi over 15 times 10 to the 8 meters squared. Let's all punch it just like it was the test. Alba, part of practicing is punching. And feel free to let me know, Alba, if you're not getting the right answer.
Brendan.
Yeah. Oh, sorry. I didn't realize you got, I can only see a few of you at a time. Let me go to the tile mode here. I was trying to stay out of your way. Excellent. Excellent. Joel, yes. Evelyn, yes. Laura, yes. Jose, yes. Will and Shay?
I haven't even seen the board long enough to even write down.
Good job, Jose.
Yep. And Shay got it too. So Will, can we just get you two? And Alba, you can try typing in what you got.
I can't even see what it says. Does that say 160?
Yeah. It looks really clear on my screen. Is it not clear on your screen, Will?
It's just really tiny. That's all.
All right, let me fix that.
Struggle.
Sorry, as I run out of board space, I start writing tinier. Is that more legible for you?
Oh yeah, that's way better. Thank you.
Meanwhile, you could try to do question 2 while we're waiting for Will. See if you can figure that out without me.
Jeez, I don't know if that's right or not.
Show it to me. Go on, Will. Something went awry. Let's try that again. Okay. 5, 8. Yeah, but there's 3 more digits you forgot there, Alba. The decimal place is Alba. Look at your number versus mine. There's 3 more digits there. You should have written it in scientific notation. You forgot about the 242. Yeah. Okay. Well, Alba, let me show you how you should have. Oh, sorry. Was that Cameron? I'm sorry. I'm sorry, guys. Can I show you guys how you should have typed that into me since you're typing? You should have typed 5.7 times 10 to the power of, what's my power? 8. That's how you should have done that. Will, do you need to punch through? Okay. You keep getting to the power of 10. You're doing something. You're not typing times 10, are you? You're not doing something whack like that.
I didn't think so.
Here.
I'll try again.
No. Just the faster way to do this, Will, is just to punch everything that I punch. So you ready to follow me?
Yeah.
Okay. 160. Wait. Fuck. I can't see this. 160, right?
Mm-hmm.
EXP 28 divide by 4 divide by pi divide by 15 exp 8 square key and then equals. Oh, wait a minute. I made the same mistake that you did. What did I do?
Yeah, that's what I got.
Oh, it's 26. I see. Everyone was. It's 26, first of all. Right?
There we go.
That's the problem.
160 exp 26 divided by 4 divided by pi divided by 15 exp 8 squared. All right, try that.
That's now we got it. What happened, Will, is when I was rewriting, I had a brainurism and I changed 26 to 28.
Okay.
So I would have written that as 5.7 times 10 to the 8 watts per meter squared. Right? Okay, now let's try the second version. In the second version, the luminosity is the same, but now our distance, I'm going to do the next one for you because we have to kind of move fast. The distance is 25 light years. So I would multiply that by light years to meters. 1 light year is 9.5 times 10 to the 15 meters. And that gives me
237.5.
Well, it has to be more than that, right?
Well, 237.5 times 10 to the 15th.
Yeah. And if I just plug it into the calculator for fun, let's just make it 2.4 times 10 to the 17. What you said is 100% correct, Joel, but I'm just doing it this way for the hell of it. And now we'll plug in the brightness. This time it's luminosity over 4 pi d squared. And so what I'm going to plug in is 160 times 10 to the 26 watts divided by 4 divided by pi divided by 2.4 times 10 to the 17 meters squared. And when I plug that in, I get 2.2. I'll just make it 2 times 10 to the minus 8 watts per meter squared. It would have been much nicer to let you guys do it, but I don't have time for that because you guys are a little bit slower than me. By the way, Will, I want to apologize for the SWEARING earlier. I'm used to.
Oh, you're good.
I'm used to being a little fresh in class because I'm used to some salty adults, and I like to keep the language kind of earthy. And I forget that some of you are parents at home with your kids. I really need to be more mindful of that. That's a good reason for me to clean up my act. Okay, I hope that helped everyone illustrate the kinds of problems you might be asked to do. I think you can do them. You guys are just a little slow because you're still thinking your way through them. And that's fine. As we do a few more problems, you'll get faster and faster. I do need to kind of change tack for a moment here. Okay. When we deal with brightness or luminosity, we're dealing with big beams of light. Or even if they're small beams of light, we're usually dealing with beams of light that contain many, many bundles of photons. So a picture that I like to show in this section is just, I have you think about like a church window with some light coming through. This is a macroscopic sense of how we talk about light. If I was analyzing this beam of light coming through a church window, I'd talk about it in terms of the brightness of the beam in watts per meter squared. But that's a little bit different than when we talk about the world of atoms. You guys will remember that light is an electromagnetic wave, and light comes from electrons doing jumps inside of atoms. I don't know if you guys remember this picture here, but we developed a picture in our last class where an electron drops from a high orbit to a low orbit, and it emits an individual photon or an individual packet of light. These photons are unique little particles of light, little packets that have a unique wavelength, a unique frequency, and a unique energy. Obviously, because we're dealing with just one little packet of light, they have very small energies in comparison to the sorts of energies we were talking about a moment ago. Light is an electromagnetic wave. And here's our cartoon picture of an electromagnetic wave. An electromagnetic wave has an electric field and a magnetic field. And to help you to understand how this works, I'd like to call on one of these little programs that I have, the physics Java apps, which I think would be instructive here. And the one that I want to choose is a radiating charge. I didn't fully comprehend this picture until I was in grad school, so it's a real pleasure for me to show this to you. Okay. Do you guys see my proton here? My proton is, oh, now we got the kitty in the screen. My proton is surrounded by an electric field. If you want to know what the electric field is, think of it as the essence of charginess that surrounds my proton. In a way, the electric field is deeply related and similar to the magnetic field. If I push two magnets together so that their north poles are rubbing, you can feel that invisible force. And that's quite similar to the electric field in some ways. Now, the electric field itself is not light. It is a force field. But if you take your charge and you accelerate it or wiggle it, you can create waves in the electric field. And this is light. Photons or light are waves of in the electromagnetic field. I've got a great demo in class where I take a big spring and I make some waves in the class. But no matter how I tried to wrap my mind around it, my screen is just too small for me to do an effective demo. Or I'd have to put the computer on the other side of the room and I'd burn like 20 minutes of class time. It's not worth it. Now, the difference between a train of light and individual photons is kind of like this. If I take my charge and I continually oscillate it, for instance, let's give it a sinusoidal oscillation. Notice I can adjust the amplitude, which is like the intensity of the wave or the brightness. The frequency is how fast I wiggle it. So notice as I wiggle the wave, let's get the amplitude really low so we can see the wave effect. You can see the wavelength here is about, I actually can measure it with my drawing tool. It looks like the wavelength is about that long to me. All right? Let's change the frequency, and you'll notice that it changes the wavelength. I might have to grab the amplitude here. Notice that at a low frequency, the wavelength is much longer. Now let's make the frequency wicked high. Oops. Ooh, that's nice. Notice now that the wavelength is shorter than it was because I've increased my frequency to the max. This is a continuous wave of light. Now let's try to make an individual photon. An individual photon I can make by just one bump. Ba-dink, there it goes. You'll notice that the photon still has a wavelength, ba-dink, but now it's just a single photon propagating out in space. Ba-dink, ba-dink. Okay. Where do photons come from? Photons come from atoms in a process called emission. Oh, one other thing. Because there are a variety of different types of photons with different types of wavelengths, the entire electromagnetic spectrum is the totality of all the types of light. One of the first peoples who did experiments in optics was none other than Isaac Newton himself. And Isaac Newton did this really brilliant experiment. Let's find it here. He took white light and passed it through a prism. Unfortunately, this is another demo that I love to do in my lectures that just doesn't work as well at home. I don't have a light source that's bright enough or collimated enough. But if you pass a really bright light source through your triangular piece of glass, you'll find that the glass will separate the beam of white light into a whole rainbow of colors. And I want you to notice that the order of colors in the rainbow is always the same. Depending on which way you flip the prism, you can either get purple on the left or you can get red on the left. But the order of the colors is the same. Red, orange, yellow, green. In Isaac Newton's day, blue wasn't all of this stuff like it is for us. Blue in Isaac Newton's day was like a sky blue or a cyan. So this was blue in Isaac Newton's day right here. This color was not referred to as dark blue like it is by us. This color here was called indigo. And I have a personal crusade to bring back the color indigo. Let's see if I can make some indigo here. Well, I don't quite have the Pantone, but I'll try it.
That's my favorite color, indigo.
Indigo is wonderful. It's a deep, rich blue. There's a cool Wikipedia page about the history of indigo and what types of exotic dyes would be used for it. It is a magical color. Now, because color is psychological, there are different shades of red, but we don't always do that for red. Like most people would say, that's red, and it's all just freaking red, right? But here we've differentiated. This is cyan or blue, and this is indigo. Whatever. Let's talk about this. This is the visible continuous spectrum. And these are the wavelengths of electromagnetic radiation that your eyeballs are sensitive to. So Newton used a prism, and with his prism, he discovered that white light can be broken apart into what is called the visible continuous spectrum. If you guys are wondering what a spectrum is when you take a beam of light and you break it apart into its component wavelengths. And the visible continuous spectrum is just another word for the rainbow. So whereas before you would have called a rainbow, now I want you to refer to a rainbow as the visible continuous spectrum. The order of the colors goes something like this. Violet, indigo, blue, green, yellow, orange, and then red. Now, most engineers refer to this spectrum by an acronym which has red starting first. They call it Roy G. Biv. Now, I don't know why engineers like to start with red on the left. As an optical astronomer, this offends me deeply because the wavelength of violet is 400 nanometers. The wavelength of red is 700 nanometers. And green has a wavelength of approximately 500 nanometers. I much prefer the acronym VIBGYOR because I like to have increasing wavelength going left to right. But I am a weirdo for saying VIBGYOR. All the other physicists say Roy G. Biv, probably because it's catchier. I just wanted you to know that if you ever see a nerd walking around with a t-shirt that says Roy G. Biv, he's probably into optics or something like that. Okay. Your eyeballs are sensitive to this range of electromagnetic radiation. There's a reason for that, but I'll get into it later. But there are other types of light besides the visible spectrum. There are non-visible wavelengths of light, as most of you probably know. I'm guessing you've heard of infrared and radio waves and gamma rays and X-rays. If you haven't, you've heard about it now. The totality of all the types of light is called the entire electromagnetic spectrum. And the visible domain is just a narrow part. So here's my VIBGYOR. Sometimes they call it the visible spectrum. Sometimes they call it the optical spectrum. It goes from 400 nanometers to 700 nanometers. At longer wavelengths, we have the infrared and the radio regime. I think the radio cuts off close to 1 millimeter, 1,000 micrometers, or 1,000,000 nanometers, where I've used micrometers and nanometers. Here are your conversions up here. 1 nanometer is a billionth of a meter. 1 micrometer is a millionth of a meter. On the short end of the spectrum, before violet, we have ultraviolet, and then we have X-rays, and then we have gamma rays. So this section is the gamma ray. I'm doing this kind of quick, guys, so. This section is X-ray, and this is ultraviolet. The cutoff on this end is 10 nanometers and 1/100th of a nanometer. I'm worried that Will's going to have a hard time reading this. Will, there's a lot of information I'm trying to pack into a single board here, so if it's too small, Will, feel free to use the EM spectrum that I have here on slide 63.
Thanks.
I'm not going to lie. Here's fair warning. I am testing you on the electromagnetic spectrum. I kind of need you to memorize this, okay? Because we need to talk about this a lot. The electromagnetic spectrum, it's the periodic table of elements, but for light. And it's so intense, and there's so many differences between the way different types of photons act, that some astronomers just spend their entire career only working in one regime of the electromagnetic spectrum. For instance, here's a book. When I was a student at the University of Arizona, there was a legendary astronomer. He wrote this book. His name is George Reiki. And he is a radio and infrared astronomer. He only works in radio waves and infrared. And he wrote the classic textbook on radio astronomy and infrared astronomy, The Detection of Light from the Ultraviolet to the Submillimeter. In other words, he was saying, I'm only fucking interested, I'm only freaking interested in astronomy if it starts above 700 nanometers. But if it's below that, optical astronomy, one of my radio astronomers, he once said to me, optical astronomy sucks. You can't see anything in it. As if to say, for him, it was vulgar to even consider looking through an optical telescope with your eyeball. That was vulgar to them. You gotta get people, this stuff goes deep, okay? There is no end to the bottom of the well that is nerd, okay? And honestly, sometimes it's kind of cool to go down there. I'm trying to explain to you that these regimes of the electromagnetic spectrum are really important to astronomers because you don't just have to look at stars and galaxies with an optical telescope. By looking at different wavelengths of light, you can see different aspects of the physics and learn more about what's going on. So it's actually a cool thing. It's not a bad thing. Classic book on infrared astronomy right here. In fact, yeah, from ultraviolet to the submillimeter, I actually screwed up, didn't I? This is optical and this is infrared, but he didn't include radio astronomy in there. So he was dealing with these two bands only. We sometimes call them regimes of the electromagnetic spectrum. Here's a $10 word for you. Regimes of the electromagnetic spectrum. All right. Let's take a look at how some photons are produced inside of atoms next. I've got time for one more thing. I'm erasing. All right, let's do a story about how the process of emission takes place. Emission is when a photon is produced when an electron drops from high to low orbit inside of an atom. And the photon that is produced is sometimes known as an emission line. An emission line has a unique wavelength, frequency, and energy. In a way, class, if I take this laser and I make a green laser dot on the board, that is an emission line because this light source has a unique wavelength, frequency, and energy. The wavelength is 532 nanometers. So a laser could be considered an emission line. I don't want to talk about this green laser. I want to talk about a very legendary emission line. It's known as the 3-to-2 transition of hydrogen. Do you guys remember what a hydrogen atom looks like? What's a hydrogen atom like? Sorry, Joel?
One proton being orbited by one electron.
Beautiful. That's the standard protium. Now, at the beginning of my tale, students, the electron is not to be found in the ground state. So the lowest orbit, n equals 1, is empty. And the second orbit, n equals 2, is also empty. At the beginning of my tail, the electron is found at the n equals 3 orbit. But it got kicked up there by a collision with another atom or something. And it's been orbiting around the atom for about 10 to the minus 5 seconds, during which time it might have orbited 50,000 times or more. And some mysterious thing that we don't fully understand, causes the electron to get tired and to drop back down. So it kind of goes from orbit 3 to orbit 2. And it's going to lose some energy when it does that. And when it loses energy, it's going to emit a photon of unique wavelength, frequency, and energy. And this photon is sometimes called the 3-to-2 transition of hydrogen. It's an emission line. Our goal is to calculate the wavelength, the frequency, and the energy. Now, let me give you the energy of the drop really quick. What's the conversion to electron volts? It's 1.60 times 10 to the minus 19, right?
Sounds right.
Okay. Let's take a look at the energy levels of a hydrogen atom real quick. Here's hydrogen, and here are the energies in electron volts. If an electron drops from orbit 3 to orbit 1, how much energy will be released? One rule about emission lines is this: the change in energy of the drop will be equal to the energy of the photon that's emitted. So the energy of the drop is the difference between energy 3 and energy 2, the potential energies, 12.1 eV minus 10.2 eV. What does that give us?
2.1.
Huh?
2.1 EV. No, 1.9.
It would normally be 1.9. Today, I'm going to do something that's a little more rich than our average problem. I need a little bit more precision than this can give us. So even though it is 1.9, I'm going to give you a couple of extra sig figs. 1.894 eV. And I'm giving you those extra sig figs because I want to get a really precise answer here, at least to 3 or 4 sig figs. So this does round to 1.9, does it not? The problem is the slide that I had only had 3 sig figs and I needed 4. Okay. Our job is to find the wavelength, the frequency. Let's just find the wavelength of the photon. How would I do this? Now, Alba, you wanted to have more example problems? This is exactly the kind of problem I'm going to make you do in the test. If a photon has an energy of 1.894 eV, find the wavelength of the line. Class, what do I do? Walk me through it and we can take some tea break.
But wouldn't the formula be E equals H times C over
Beautiful.
your upside down Y?
Lambda. Or just call it wavelength. Joel, you are crushing it, my friend. That's exactly what we want. But Joel, we have the energy. We need the wavelength. So how do I rearrange it?
So the wavelength is.
You know.
Oh, okay. So it would be. Oh God.
Can you flip a burger? Then you can flip an equation. This.
Oh yeah. So So if you flipped, so it'd be E over H times C.
No, that would give you 1 over lambda. If you put those down there, you have 1 over lambda. Lambda's in the bottom. You should flip lambda up and E down, right?
Sure.
That's
Because I'm obviously saying it backwards, and you're correcting me. So yes.
Right. So can I explain why? In the previous question, like if you do this, then your wavelength is on the top, and then it makes sense to flip down the lambda. But in this case, you have E equals something over lambda. So the lambda should flip up, and the E should flip down.
Yeah.
Did that make any sense?
Yeah, yeah.
All right. So what's my final equation then? It's
H times C over E.
good. Okay, now what?
I could be wrong, but I thought the equation was E equals H times C over F.
That would be incorrect. And if you want to know why, the two formulas that you start off with, Evelyn, are C equals wavelength times frequency, and energy is Planck's constant times frequency. This is a famous formula called the photoelectric effect. If I solve this for frequency, I get frequency is C over lambda. And then you plug C over lambda into F, and you get HC over wavelength. This is equation, it would be impossible for me to screw up because it's so central to much of astronomy knowledge. This is one of the reasons why you're learning it.
Okay, got it.
Do you trust me enough now?
Yeah.
You should always verify it for yourself. And by the way, as we've discovered, Evelyn, I make tons of mistakes every class. So you should always question me, okay? Because half the time you guys keep me from the screw ups. If you don't speak out, we won't catch them. All right. But you're good now, right, Evelyn?
Yeah.
Okay. Okay, so then Evelyn, while we're talking, what should we do next?
You just plug in your values, so you do. Well, would you have to convert something first?
Yeah, what? I want you to find it.
You'd convert the 1.894 EV into joules.
Excellent. And you guys are going to have to remember to do this stuff. Actually, you might not even have to, because you know how I told you it's multiple choice and I break down the questions into parts? Usually the first part of the question will be convert electron volts to joules, and then the next part will ask you to use the formula. So I kind of try to walk you through it. So let's do that up here. Evelyn, how do I convert 1.894 into joules?
I'm looking for the, okay. So it'd be, you put EV on the bottom and joule and J on top, and then 1 on the bottom is equal to 1.6 times 10 to the negative 19th joules.
I'd like to point out it's 1.60, so we keep some extra sig figs. Give me 3 sig figs. What'd you get?
You say 3 sig figs?
Please.
3.03 times 10 to the negative 19th.
Units?
Joules.
Good. All right, so now what am I going to do? You feel confident? You want to keep going?
Sure. You would do lambda equals.
Okay. We usually, in this class, during the exam, I usually give you a really rounded, crappy version of Planck's constant of 7 times 10 to the negative 34 joule seconds. That's because I'm trying to get you guys to think about the concepts and not get hung up on the third decimal place. But I've got to say that Planck's constant in this problem, we actually need a few more sig figs. Did you guys watch Stranger Things? Anyone?
Yeah.
It was kind of a cool like sci-fi show on Netflix. I liked it because it was. Wait, someone's chiming in on the chat here. Let's see who's. I bet they're a fan. Alba saw it. Yes. What was cool about Stranger Things is it takes place in the 80s, and it's all these kids, and it's kind of like an E.T. kind of monster movie, like a Spielberg 80s movie. And they did the period piece really well because the kids who were riding around on bikes, like I had those same bikes that they had, and like their tube socks looked like my tube socks. So it was kind of nostalgic for me. One of the plot points in the third season was that they had to unlock a safe. And in order to unlock the safe, you had to know Planck's constant to 6 decimal places. And of course, one of the little nerdy girls knows it, and so they can unlock the safe. Now, I usually just ask us to know 1 sig fig. So I actually round 6.62607 as 7, just because who cares? In today's class, I think we should try to use 3 sig figs because I'm trying to do something a little more precise. So to 3 significant figures, Planck's constant is 6.63. And I want to use that today. So Evelyn, lambda is 6.63 times 10 to the negative 34 joule seconds times, believe it or not, the speed of light is good to 3 decimal places. By design, it's 3.00 times 10 to the 8 meters per second. And that's going to be divided by 3.03 times 10 to the minus 19 joules. Go ahead and punch that up for me. I'm going to give you a tea break, but I need to finish this point so I don't lose the thread of it. Hey, Jordan, could we get a little airco going? Maybe 72? Thank you so much. Starting to get the hot and sweaties here. You guys got something for me? Looking pretty good, Evelyn. I like it. Everyone else want to show me too? Joel, yep. Laura, I'm looking. Laura, it looks like you got it right. Yeah, you got it. How about other Will? How about Shay? I don't know if it. Yep, Shay, you got it. Oh, season 4 is coming. Hey, Alba, what'd you get for your calculator later? Calculator. Jose, we lose you too? Who else is in here? I think everyone's looking for a break, and that's fine. I just wanted to finish this before we did it. So, Evelyn, give me what you got.
6.55 times 10 to the negative 7th.
Round better. It's 6.56, right?
Yeah.
Right? This is what I got.
Yeah.
So that's 6.56, right?
Yeah, I got confused because I thought if the digit after the 6 was less than 5, then you would round the 6 to a 5.
No, you never go down. You leave it flat or you go up.
Okay.
Think about it like dollars and cents, Evelyn. If I had $656.40, is that closer to $656 or $657?
$657.
No, $656.40 is closer to $656, right?
Yes.
Do you follow me or am I losing you?
No, I got it.
Would you say it's closer to $655? Never, right? Okay. Okay, now for the follow-up questions. How many nanometers is this? Could you do that without my help?
You just had 3 zeros, right?
Whoa, there's 2 Wills. Oh my God, this is insane. Did you just clone yourself and jump through the multiverse? I was about to be like, Will, what did you get? And Will, what did you get? I'm sorry, what did you say, Joel?
Don't you just add 3 zeros?
Can you just tell me what the answer is in nanometers?
656.
That's right. Now, on the test, I would ask you this question. In what regime of the electromagnetic spectrum is this photon found? In what regime of the electromagnetic spectrum is this photon found?
Red.
Yep.
Or
Red isn't a regime. Red
oh,
is,
I see what you're saying.
what do we call that regime?
The visible.
Yes. And what's the color?
Orange or red?
Red. It's a deep red. I'll tell you more about that photon after a tea break. I've got a cool story to tell you, but I kind of feel like everyone's starting to get fuzzy here, low blood sugar and all that. There's a lot to say about this, and I've got some cool demos to show you. Should we take a little pause? Oh, we got another youngster there, Will.
They're
You got a full house,
multiplying.
don't you, Will? Cats and little kids? Oh, I couldn't hear you, but I can see by the look on your face that it's a lot. I think the mic on your iPhones might not be working. I don't know. Can't hear you, no. Yeah. You guys want to do a little pause and chill for a little bit? Oh, Will, did you have trouble getting that answer? Will, for some reason I can't hear you. I don't know. I don't know if you're talking to me or talking to someone else. Well, okay. We see you, Will, and we are here with you. Whatever you're trying to say, I have no idea, but feel free to chat it in the chat box. Why don't we take a little pause? I think I could use a little break until about 2:15 or so. Take a half an hour. All right. Well, maybe you can figure that out during the half an hour. I'll be around. Peace.
So, Brendan.
Will said I need a break. Yeah, what's that?
So, I don't know what I'm doing wrong.
Okay.
In terms of translating the meters to nanometers.
Sure, I can show that to you. I want.
Did you give us the conversion?
I did somewhere, but I did it kind of sloppily.
Okay.
Let me walk you through it nice and slow. The conversion is 1 nanometer is a billionth of a meter, 1 times 10 to the minus 9. So you would go 6.56 times 10 to the minus 9 meters. Meters on bottom, nanometers on top. 1 nanometer is 1 times 10 to the minus 9 meters.
But isn't it 6.56 to the negative 7th?
It's 656 times 10 to the minus 7th. Or 656. Oh, I'm sorry. Whoa. Yes. I'm sorry. Yes, dude. I apologize. I was bouncing back and forth in my head. too quickly.
Okay, so it's one nanometer equals. Oh yeah.
Does that help now?
So the 1 times 10 to the negative 9 meters. Okay.
In other words, watch this, Will. Do you see how it's 6.56 times 10 to the minus 7? That's 65 times 10 to the minus 8, or 656 times 10 to the minus 9, or 656 nanometers.
Yeah.
In any case, if you use the dimensional analysis, you can't screw it up, as long as you have that conversion factor.
Yeah.
And as long as you don't do a stupid thing like what I did there.
Yeah. I'm just having a really bad math brain day. It's horrible.
Just get a little sugar in your brain so that it kicks on again. I'm the same way. So after the break, we'll talk. We're gonna stay on this problem for a minute when we come back. Okay.
Okay.
All right. I'll see you in a bit.
All right. Cool.
I'm pausing. Hello, everyone. I'm back. Hey, do you guys want to see something cool?
Back
Something
to
really moving? Oh, you're back too. Hey, Jose, you figured it out.
yeah.
Do you guys, you know how I showed you those videos of the looting and stuff on our last class? Do you want to see what's happening in the storefront right now? Because it's really cool. I just noticed this during the break, and I think considering that you guys had a buy-in for the last one, you should see what's happening because it's really awesome. So I don't want to spoil the surprise. Let me just share. I have to install the dumb widget again. It makes me install the widget every time. I don't get it. Okay, so sorry. All right, check this out. You ready?
Oh, nice.
That's so dope.
That's
Oh my
cool.
goodness.
Nice.
Isn't that rad?
That is so rad.
Isn't that so cool?
It's a
Yeah.
great
I was like,
answer.
what a fucking cool response, and what a cool
Yeah.
way.
That
What a,
Great response.
what a cool way to respond to it, right?
Yep.
Yeah.
How's the raccoon doing?
I think he's okay.
Yeah.
Wait, what?
Well, he
got a
wasn't
raccoon?
around yesterday. I think he was scared by all the looting, so he was kind of hiding out, you know. But I didn't get to feed him yesterday because I was too busy. But I'll try to feed him after class and see if he's around.
So they
they're
don't know
basically right
about
on top. They're right on top of him.
Yeah. He lives in the sewer right by his place. The rest of the class doesn't know about him because that was our last semester. We talked about the raccoon.
Exactly.
Oh.
Exactly. Yeah. No. Oh, that's right. I forgot that they don't know about him. Right. Yeah. The raccoon lives in the sewer, right underneath that mural.
You go down into the sewer to feed a raccoon?
Kind of. Like I have a little grabber, and I put chicken on the grabber, and I put it into the sewer, and he eats it.
That's awesome.
His name is Buff. He pokes his head out when I walk by, and he puts his paw out and gets a little piece of the food. You guys didn't.
Now, does the raccoon come when you say Buff?
I go, pss, pss, and then he sticks his head up.
Oh,
okay.
Wait, I wonder if. Hold on,
that's adorable. I thought that you like physically like went down into the sewer to feed this raccoon. I was like, whoa, man.
Wait, hold on.
Shay, Brendan's not in the military.
What's this?
That's right. Only us idiots would do that.
Wait, I'm sorry. Okay, here, hold on. I'll try to. Oops, I don't want to end the meeting. I really should not be. I should not be goofing around like this. But hold on a sec.
It's still break time.
Yeah. Shit's too heavy today anyway.
Let's see if I can. Oh my God, it's really noisy out there. Hold on, I gotta.
Oh, my head actually hurts from thinking.
Yeah, this is, I'm cross-eyed. More than usual.
Joel, your dog looks like you. Has anyone ever said that before?
I don't think so, but
No?
they do say that you and your pets start to look like each other.
Totally.
So what are you saying? That I'm lazy?
How old is
He's 5.5, and he's my service dog. So people see, like, if I stand around and talk, he just lays down, and people are like, or like if I'm just sitting at when I worked at the hospital, people be like, well, he's not really working. He's just sleeping. And I'm like, I don't need him to work right now. If I needed him, he'd jump up and.
Yep.
Oh,
Part 2.
You feed him a whole slice of pizza?
Oh, this one was epic.
Delivering him a pan of pizza. That's awesome.
What areas?
Oh my
Ready?
God.
Someone been feeding you.
Dry ramen.
Look at this.
God.
You're being so rotten, huh?
Someone was feeding him ramen.
You don't want the pizza?
Oh man.
Oh, I'm loving the commentary.
Oh, yeah.
Oh, he takes the ramen. Hey, come get the pizza.
He comes out with this. There's a couple of failed ones.
Have you ever gone out there and just like a little clown shows up?
Say that.
Oh God.
Have I ever
gone? Have you ever gone over there just like a clown shows up, like asking you to reach your hand in and something?
Well, I did. Did I tell you that I put my cell phone on a dowel and I poked it into the den? That was one of the most epic videos ever. So here he is. Here he is. He's gonna take the pizza. Watch this.
Fuck that. Oh my God, someone gave him ramen. Okay, hey, look, do you want to try some pizza? Come on, get some pizza.
Aww.
Huh?
Awesome.
Yeah. Get that pizza.
This is what I do in my free time, guys.
How cute.
People are driving by like, how's he doing?
My friends were like, why do you feed the raccoons such a bad diet? I was like, I guess because that's what I eat.
They eat trash.
Yeah,
they love trash.
I know. It's like my diet's pretty much the same as the raccoons.
and Brendan, your voice sounds so demonic when you're like trying to get him to take the pizza.
Yeah.
Come on, take the pizza.
The best one was I attached my phone to a stick and I wanted to see what it looked like inside of his den. So in this video, I went into the lair of the raccoon, and this is I think the one. I think this is the one where I went into the lair.
All right, can I see that?
Yep.
Thank you.
I think we were feeding him a cookie or something. What is that? Oh, it's a piece of chicken. It's a chicken wing.
Look at
Chicken
you.
wing, right?
Look at you.
Oh, he's waiting.
You are just chomping at the bit.
Oh,
You get a little more chicken on the stick, huh?
It's dinner time.
It's dinner time.
Try that?
Yep, give me it. Thank you very much.
You have fun with that in there.
All right, watch this.
Aw.
But this time, we're coming with you.
Wow.
Little house tour.
He's got a damn arsenal down there. He's got
I
milk
know.
waiting.
That dirty little nest.
Wow.
You know what? In these difficult
Amazing.
times, guys, we need ways to entertain ourselves, and this is what I got. That's my neighborhood, you know.
That's awesome.
I'm gonna have to start watching the news just to see if the cops catch you doing that.
Yeah, exactly. Okay, I'm sorry for that diversion there. A little fun never hurts the day. Doesn't help the day. Does not hurt helping the day go by. You know what I'm trying to say. Okay. I want to talk about the exercise that we did just before lecture. So what happened here? What happened here is we had a hydrogen atom. And the hydrogen atom, right, has an electron which is dropping from orbit 3 down to orbit 2, and it's emitting a photon. The photon has a unique energy, a unique wavelength, and a unique frequency. You guys calculated it. And what did you discover about the wavelength and the frequency of this photon? What did we learn?
That it was visible.
It's in the visible regime, and it has a color and a wavelength of
56 nanometers in red.
Yeah, and let's look at where that is in the visible spectrum. If you come over here, and I click ahead to the visible continuous spectrum, you can see that 656 nanometers, this is a true color one. It's about as red as the day is long. Let's see. This is 20, 40, 60, 80, 100, right? So 656 would be, this is 640, 660.
To the left.
It's somewhere around here,
Left.
right?
You're already on 650. Your last big hash. Is
Oh, wow, I'm dumb. Sorry. 650, 60, 70, 80, 90. I'm sorry, I had a dumb moment there. 652, 654, that's 656 right there. So that's the color. It's a pretty deep red, maybe a touch orangey, but it's red. Similar, honestly, to the color of this crayon right here. Now, why this is so important is this single wavelength of light, 656 nanometers, is one of the most legendary emission lines in all of astronomy. And let me show you why this is so important. I want to take you out to a beautiful place called the Rosette Nebula. So let's fly into outer space. Let's go visit the Rosette Nebula. Deep in space, there's a cluster of newborn stars which are currently surrounded by a massive cloud of hydrogen gas. And this cloud of hydrogen gas, known as the Rosette Nebula, is being heated up by ultraviolet photons from these big bright blue stars that you see here. And the gas is being heated so that all of these hydrogen atoms, the electrons, are being excited up to the third orbit state, the third orbital level, where they orbit around for 10 to the minus 5 seconds or so, and then all of the atoms all throughout here all begin to cascade down at once and emit light. But they're not just emitting any color of red, they're all emitting the 3-to-2 transition of hydrogen. They are all emitting hydrogen alpha photons. So this nebula that you see here, it's not just a red nebula, it's a laser nebula. All of the light coming from this nebula is at exactly 656 nanometers. So think about how cool that is, right? Like, the stuff that's happening at the most microscopic level, the 3-to-2 transition of hydrogen, is producing this brilliant and awesome looking red nebula. So you can see what's going on in the quantum world of atoms is affecting the most epic, large-scale grandeur of space. For this reason, these types of nebulas that glow with this red light are known as emission nebulas. And this photon is a legendary photon known as hydrogen alpha. Hydrogen alpha, otherwise known as H alpha, is the 3-to-2 transition of hydrogen, and it has a wavelength of 656 nanometers. It has a red color. This is good to know. Now, we calculated the 3-to-2 transition, but the electron could have then dropped from 2 to 1, emitting another photon. It also is possible for the electron to drop directly from 3 to 1, right? Like, many different transitions are possible. How much energy would a hydrogen atom expend if the electron then drops from orbit 2 to orbit 1? Let's look back at the picture here. According to my diagram, we lost in cascading. I'm doing this kind of slow because I want to make sure I don't lose you here. In dropping from orbit 3 to orbit 2, we lost about 1.9 electron volts, and that produced a red photon. How much energy would you lose if you went from orbit 2 to orbit 1?
10.2.
Exactly. Now, I could make you convert that into a wavelength again by doing the same exercise, but that took a little while. So why don't I just show you the results instead, and we'll talk about it. This diagram attempts to show you all the different possible transitions an electron can make inside of a hydrogen atom. You were just studying the 3 to 2 transition, which produces a red photon known as hydrogen alpha, 656 nanometers. However, you'll notice, for instance, that the 4 to 2 transition, had an electron dropped from orbit 4 to orbit 2, would produce a photon at 486 nanometers. And that would be a blue photon. That's a blue emission line. People call that hydrogen beta. So this is hydrogen alpha.
Not to be confused with indigo.
This is more of a cyan color. In my experience, Joel, indigo is a deep blue that's right at 450. I can tell you, you're going to look at this in a moment because I'm going to show it to you. This blue photon is a cyan color. Some people even confuse it for green. You'll notice indigo, Joel, is kind of over here, but this is a proper blue. So if we're going to get into shades of shades, then yes, blue. Notice that also it's possible to have an electron drop from orbit 5 to orbit 2. That produces a photon at 434 nanometers, which is in the violet/indigo portion of the spectrum. To your eyes, it looks pretty violet. Taken together, this photon, and this photon make up what is called the emission line spectrum of hydrogen. In other words, you know how if you take a light bulb and you break light into its component colors, you'll get a rainbow? Pure hydrogen gas does not produce a rainbow. It produces very unique emission lines, and they are being powered by emission. Okay, now you guys try it. Suppose the electron dropped from level 2 to level 1. What wavelength of photon would it produce? I just want to see if you can follow me here. If an electron drops from orbit 2 to orbit 1, it will produce a photon of what wavelength?
121.6.
Am I sharing my screen with you guys right now?
Yes.
Yeah. All right. 121.6 nanometers. Shay, in what regime of the electromagnetic spectrum is a 121 nanometer photon found? I'm going to ask you these types of questions on the test.
I just had it. Wait a second. 126. That would be
Nanometers.
Right, nanometer. Oh yes. Is that infrared? How many? 121.
121. Remember, Shay, infrared is over here past red.
Oh, I have the opposite. 121, got it. Oh, UV.
That's right. In this direction, we go towards the ultraviolet. And short of 400, this is an ultraviolet photon. In fact, do you want to know something cool? If we look on the internet, we should be able to find a picture of the Rosette Nebula in the ultraviolet, and then we'll be able to see the 2 to 1 transition. So here's the Rosette Nebula in the optical, and here's the same nebula, the Rosette Nebula, but now in the ultraviolet. Oops, sorry. Notice when you see the Rosette Nebula in the ultraviolet, you are seeing the gas from a totally different perspective. You'll notice the stars are not quite as bright in the UV, and that you're getting this intense UV emission from all of the 2 to 1 transition. You can look at different aspects of the gas by looking at different wavelengths of light. Now we can see the 2 to 1 transition of the gas. Very cool.
Well, Brendan.
Yeah.
Would the stars still be just as bright, but just the gas that's being emitted changes the perspective on the brightness? Because
no, stars are something called a black body. And black bodies emit colors that depend upon their temperature, and the colors are not flat. Joel, that's a fantastic question, and I'm building up towards the answer, but I cannot answer that just yet, and I will answer that before the class is over. Okay, so just
that was good enough. I mean, it based on temperature, the body emits
different amounts of light
under yeah. So
even
okay, yeah, that makes sense.
Even a single body at temperature. So I have a slide on it. What I should do is I should just show you the slide. Even a single temperature object does not emit all the colors equally. They emit as a black body. Wait, let me just show you here.
Like on a thermal imager, we'll have higher, stronger colors than others, and
right.
Based on the temperature.
This picture shows you brightness as a function of wavelength for 3 different stars: a blue star, a yellow star, and a red star. You'll notice they have this characteristic shape, which is known as a black body profile or a Planck function. Red stars tend to peak at the red end of the spectrum, sometimes even in the infrared. Really bright blue stars tend to peak in the UV. One question I have about that photograph is, I happen to know that those stars are actually really hot, bright blue stars. So you'd actually expect them to be pretty bright in the photo. I'm not exactly sure why they appear dimmer. You actually kind of stumbled onto a question that's in my mind too. The stars could appear dimmer for a number of different reasons. It could actually be a reason of photography. It could be that the nebula in the UV was so much brighter than the nebula at 3:2 that the stars artificially appear dimmer because you're exposing the photograph for the nebula. You know what I mean? There's a bunch of different, it could be complicated why the stars aren't as bright there, but it's a good question to start thinking about. Let's draw out together the spectrum. Oh, by the way, suppose I compressed all the photons of hydrogen together. What color do you think I would get? What color would you get if you mixed, oh, I'm sorry, you're not seeing what I'm seeing. Zoom. A Dyson sphere. Okay, share. Oh, a Dyson sphere, I see. You're referring to the, that Spencer gift toy thing, right? Class, suppose I put together the spectrum of hydrogen here, F515. What color would you get if you mixed all 3 of these together? Who knows their color theory from art class? Red plus blue equals?
Purple.
And purple plus purple is more purple, right?
Yeah.
Okay, no tricks. So if I can share my screen with you again, let's see here. Share screen. Let me share my iPhone. This is what we're going to be doing in lab today. And I think it's important to kind of take a moment to show you how this works. Hold on. I'm trying to get my phone under control here. Okay. Let me go over here to my drawer where I have a number of different gases. You'll notice that here I have a hydrogen spectrum tube. I don't know if you guys can hear me. I'll try to talk loud.
What? Can't hear you.
You can't?
No, we can hear you.
Oh, you could. Okay, sorry. I realized that if I walk out of the direction of the microphone, it might be hard. So here's a hydrogen spectrum tube, and here I have a power supply that's kind of set up down there. Let's turn this on. And do you see that beautiful electric color? That's a deep electric purple. Now, I have a tool that astronomers use. The tool is called a spectroscope. Oh, weird. It's frozen. Oh, there's a delay. There's a weird, wacky delay.
Yeah.
Whoa, that's a crazy delay. I thought I was like looking at a poltergeist version of myself or something. I was like, wait, how can I be seeing the tube? Never mind. This is the spectroscope, right? And the spectroscope is a tool which I can use to break light apart into its component colors. It actually uses something called a diffraction grating. A diffraction grating looks kind of like the back of a CD. Now I'm going to attempt to hold this up to the lamp, and let's see if I can actually take the spectrum of this thing. It can be a little tricky. Oh yeah, there we go. Can you guys see the, there's a bit of contamination, unfortunately, Can you see the red line, the hydrogen alpha there?
Yep.
Actually, let me get some light in the background so I can illuminate the wavelengths. This is what we're going to attempt to do in lab today. It's going to be a little tricksy, but I think we can do it. I need to be able to hold my hands real steady here. Get out of here. Can you see the purple, the blue, and the red line? Can you see it?
Yeah.
Yeah, the purple's not real strong, but it's there.
Yeah. One of the reasons why is CCD cameras, like eyeballs, have a very sucky ability to detect purple. By the way, your eye is not uniformly sensitive to all colors of the visible spectrum. Your eye is really good at detecting greens and yellows, but as you get towards the edge of the purple or red end, your ability to gather and interpret those photons drops, and it falls off even steeper on the purple end. One of the sad things about doing this lab over the internet is, one of the things I love for students to see is when they look through a spectroscope to see just how ghost-like the purple emission lines are, and how you have to like look at them and try to figure out, did I actually see that or not? That's, as Shay and Laura were lucky enough to take the course with me in person.
Yeah.
So they got to have that experience.
It was my favorite lab. That was my favorite lab, seriously.
Not only is it my favorite lab too, but it's one of the most important to understand what astronomers do. Astronomers don't just take pictures of light. They analyze light. They mine it for information. And you guys would not believe how much information you can get from light. You can get so much information. One of the ways you can do it, it's a science called spectroscopy, is by analyzing the emission lines of individual atoms. So let's kind of draw a picture of what the emission line spectrum of hydrogen looked like. Okay. So here, we have what is known as the emission line spectrum of hydrogen. And if we were to draw it out, it would be 3 different lines at 3 different wavelengths. It would be, all my markers are all over the place now. A red line at 656 nanometers, and that's nicknamed hydrogen alpha. It would be a blue line at 486 nanometers. That's hydrogen beta. That's its nickname. And the purple line that you can barely see, but you can see it, is hydrogen gamma. That's at 434 nanometers. Taken together, the red line, the blue line, and the purple line make up what is known as the emission line spectrum of hydrogen. And these telltale lines are characteristic of hydrogen. If I observe these colors in any light source, I know that hydrogen is present. What about helium? Think about it. Hydrogen is the simplest atom. It's just got 1 electron and only 1 set of jumps to make. But if you go to helium, you've got 2 electrons, which are also simultaneously jumping. Lithium has 3 electrons. Beryllium has 4 electrons, and so forth. Do I expect the 3 to 2 transition of helium to also produce a photon of 656 nanometers? Yes or no?
Not necessarily. Well, if the jumps are all the same, then
there's one difference though, Joel. What you're measuring when the electron drops from one orbit to another is the electrostatic potential energy. In a way, lifting an electron above the floor of the ground state is a lot like lifting a 1 kilogram mass up in the gravitational field of Earth. Now, remember how yesterday or Tuesday, I lift the 1 kilogram over my head. Do you guys remember how many joules a 1 kilogram squat is? If I lift this thing over my head?
42,000?
It was 20 joules. I think 42,000 was the bullet.
I think he had to do
42,000.
4,800 squats or something.
Oh yeah, it was
Yeah.
42,000 squats that I had to do. That's right. So if I lift this over my head, it's 20 joules of energy. What if I went to the planet Jupiter? Do you think if I lifted this 2 meters over my head, that would also be 20 joules?
No, because of gravity.
Because the gravity of Jupiter is greater. In fact, in the potential energy formula, it's mgh. The m is the same and the h is the same, but little g on Jupiter is not the same. In fact, I suspect that I would not be strong enough to lift this up 2 meters in Jupiter's gravitational field. In fact, the g-forces on Jupiter might be so intense that I might not even be able to stand up. It would probably crush my ass like a tin can. Sorry, crush my body like a tin can. I'm working on it. Okay, so
Interesting.
right? You couldn't even stand that easily on Jupiter, probably. Jupiter doesn't have a surface also, but let's forget about that. A platform in the cloud tops of Jupiter. So in the same way, we're not dealing with gravitational potential energy here, but if you go to helium, you know that helium doesn't have one proton, it has 2 protons. And that's twice the electrostatic attraction, and therefore it's like going to Jupiter. You'd have to lift the electron. So the jump might be the same, Joel, but the energy is not the same. And this is important because, in fact, we're lucky that they're not the same. Because this means, oh, I'm sorry, I'm trying to share my screen here. Share screen, share. If I go to 63, every atom in the periodic table emits a unique set of emission lines. Now, unfortunately, this slide I have reverses the direction of red and blue, so I'm sorry about that. This is Roy G. Biv instead of Vib G. Orr. But notice that hydrogen is still basically the same here. You guys can see, hydrogen alpha there. You can see hydrogen beta, and you can see hydrogen gamma. Notice that helium is not exactly the same. There is a red photon, but I don't think it's the 3-to-2 transition. It's something else, and it's not the same wavelength. It's different. There's also a yellow emission line, and there's several blue and indigo emission lines. Sodium is an interesting case. Sodium has almost no emission lines in the visible spectrum, except for a really bright yellow doublet. This is a double emission line known as the sodium doublet. And it's this bright yellow emission line. Have you guys ever been like cooking ramen or mac and cheese and had the salty water spill over the pot and hit the gas burner? If you have a gas stove like I do, when the salt water hits the gas stove, you see a little flash of yellow when the pasta water hits the flame. That little flash of yellow that you're seeing is the bright sodium doublet from the salt in the water giving off an emission line. Neon, of course, is famous for its crazy number of red emission lines. This is how we get the Michelob sign at the bar. When we're staring at a neon sign, we're seeing a collapse of all of these red emission lines. And so, in fact, every atom in the periodic table has a unique set of emission lines. One of the cool slides that I found at some point was the entire periodic table of the elements, but instead of showing you the elements, it shows you their spectra. And I think I have it over here somewhere. So this is a quick snapshot of all the different emission line spectrums. Notice that they're complex, but no two are alike. This gives us the ability to do spectroscopy. Do you know, if it wasn't for the fact that each atom had a unique fingerprint or a unique set of emission lines, we would not know what the stars were made out of. But I can analyze light from the stars, and I can figure out that they're made of some of the same atoms that we find here on Earth. They're also made of some of the same atoms that I find in the sun. And that means the science of spectroscopy is the act of taking prisms and diffraction gratings and taking beams of light, breaking them into their component wavelengths, and studying those wavelengths to learn about the atoms that are emitting the light. Let's take a couple of notes on that, because that's going to be really important for our class. So how do we sum all this stuff up? We can say that each atom produces a unique emission line spectrum. And this emission line spectrum is sometimes referred to as a chemical fingerprint. It's a fingerprint for atoms. Not only do atoms produce emission line spectrums, but in certain cases, they can produce what's known as absorption line spectrums. In an absorption line spectrum, instead of seeing the photons that are being emitted from the atoms absorb photons from white light. So if you have white light striking an atom, electrons can grab individual photons and they jump up from a low to a high energy state. Here you can see hydrogen alpha in absorption. A photon at 656 nanometers has been removed from the spectrum. Notice that the hydrogen atom can only grab exactly that wavelength that the electron needs to jump from low to high orbit. The hydrogen atom could not grab any of these photons because they don't have the right energy to kick an electron up from level 2 to level 3. Here you can see hydrogen beta in absorption. And here you can see hydrogen gamma in absorption. Honestly, guys, this is starting to get a little bit confusing because if you think about it, that means there are kind of 3 types of light sources that you can find in nature. Let me show you a cartoon of them really quick. You can find examples of rainbows, and rainbows are called continuous spectrum. You can find emission lines, that's an emission line spectrum, and you can find absorption line spectrum. And here's a little summary of the 3 types of spectra: continuous, emission, and absorption. The man who first figured out how to understand the difference between emission, absorption, and rainbows was a serious-looking Prussian scientist by the name of Gustav Kirchhoff. Let's look at a picture of Gustav Kirchhoff because I really got to say I like his style. I wish that scientists, including myself, still looked like this. This guy basically looks like Count Dracula. He's pretty intense looking, and I wish I had a suit like that. And that's how actually he's got a bolo tie, so we're not doing too far. Okay, so he's going to personally influence my future science style. He's a serious-looking fellow who came up with what's known as Kirchhoff's 3 laws of radiation. And the laws of radiation attempt to explain how light sources like atoms or shining clouds produce the 3 different types of spectra. This is some classic astro stuff, and it's part of our lab today, so let's get into it. And when I say spectra, you guys are understanding what I mean by that, right? Like a spectrum or a spectra. It's just it's a plot of the colors that you're seeing through your prism. It's a breaking apart of light into its component wavelengths. So light is capable of producing 3 types of spectra. The 3 types of spectra are continuous, which is a rainbow. Sorry, I moved this thing a little farther away. Continuous, emission line, and absorption line spectra. And that top word, which I wrote quite badly, is continuous. Continuous, remember, is code word for the rainbow. Let's not forget that. How do we get these 3 types? We have to ask Gustav Kirchhoff. Kirchhoff's 3 laws of radiation. These are every bit as important as Newton's laws and Kepler's laws for astronomers. There's a lot of 3 laws going around in this class, okay? The first law is called the law of black bodies. The law of black bodies states a hot, dense, solid produces a continuous spectrum. Underline hot, dense, solid, because that's the key phrase. The second law, these are testable. The law of emission states a hot, thin gas produces an emission line spectrum. Hot, thin gas. Will, I hope you're able to read these somewhat. Are you struggling? Okay. Just let me know if you need me to read any of this again. The third law is the law of absorption. The law of absorption states a cold, thin gas in front of a black body produces an, I'm running out of room here, absorption line spectrum. Sorry, I should have went back up to the top. Hello. How are we looking there? Can you guys see that? Nice. An absorption line spectrum. So just to show you that in cartoon, form, share screen.
I didn't get it copied down yet.
Oh, sorry. Let's give you a moment. Sorry, Joel, keep going there. Wow, it's hot out today, huh? I'm feeling the sweaties.
Bet your raccoon's nice and cool in his sewer, though.
Did you see the big mural up there? Yeah. It's so beautiful, right? Okay, what's that again, guys? Sorry?
So I was just saying that your raccoon's probably nice and cool in his little
I was thinking about that, yeah. Honestly, people tried at one point to accuse me of being cruel for feeding him, and I said, are you kidding me? That guy's got the best raccoon pad. He's got a raccoon loft downtown. He couldn't have it any better. No natural predators, an abundant supply of food, a ding-dong like me to feed him pizza every day. You know, and he's got a little den. He probably cleared it out of the rats out of it before he got in there.
The guy's like, a pimp. He's a pimp.
Exactly. He's a pimp raccoon. So someone tried writing me on social media. It was like, why don't you take that raccoon to the forest where he belongs? And I was like, I think he's doing just fine. I think in the forest he'd be getting eaten by coyotes and hunting around for moldy mushrooms. Now he's eating pizza and just doing the backstroke in a pile of trash. He couldn't be any happier.
Well, I live out in the woods, and let me tell you, the raccoons come in here and eat my trash. So
I bet they do.
Give him what he wants.
Exactly. Give him what he wants. He wants the garbage. I call him my little garbage disposal. Every time I've got pizza crusts and stuff, I'm just like, you know what? Buff could use this. And so I give it to him. All right, let's look at a cartoon. Did you get all that stuff, Joel?
Yeah, I got it.
We're going to be doing this in our lab today, so let's look at a quick cartoon here. So light bulbs produce white light, which you know is a rainbow. And thin clouds of gas, like the hydrogen tube that you just saw, or like the Rosette Nebula, they produce emission lines. An example you have yet to see is called an absorption line spectrum. They're kind of more complicated. What happens is you have a white light source like a star or a light bulb, and that shines through a cloud which is cold. The reason why the cloud needs to be cold is so that all of the electrons are down in the ground state of the atom where the energy is lowest. Those electrons will then grab photons from the white light and they will jump up to an excited state and remove unique photons from their spectrum. Probably one of the most important absorption line spectrums ever discovered in nature was when Joseph Fraunhofer took a prism and passed white sunlight through the prism to find the spectrum of the sun. I'm going to show you the spectrum of the sun as part of your lab today. And I'd like to show you what it looks like here from BU's heliostat. Look at how it's really hard to explain to you guys the first time around just how beautiful the spectrum of the sun is. You see a rainbow, and it's a big, bright, rich rainbow, but you can see thousands upon thousands of absorption lines. Do you see all this? This is the superposition of all the different absorption lines caused by all the different atoms in the atmosphere of the sun. So for instance, probably somewhere in here, one of these is hydrogen alpha, but the one next to it might be helium, and the one to the left of that might be from mercury or neon. You can see that the sun has many, many different types of atoms in its atmosphere, because taken together all, and by the way, astronomers have mapped out every single one of these absorption lines to a very high degree of precision. One of the classic charts that astronomers use is this one, mapping out some of the more well-known lines in the sun's spectrum. Here you can see, for instance, oh, does that look familiar to you guys? What's the double yellow line? What atom causes that?
Oh, salt.
Not salt, but, well, who?
Sodium.
Sodium, right. So sodium is Na. Let's look at line D. Yep, Na, sodium, right there, right? So you can see that they've mapped out, look, they even have hydrogen alpha here, 656.3 nanometers. That's the so-called C line of hydrogen. So this is going to be really important, obviously, because our whole class is supposed to be about learning about stars. How do you think we do it? By taking their spectrum. Wow, I didn't realize it was 306. Okay. I apologize for going on for so long. I need to do a couple of things before we break. I need to show you 2 more formulas, and I need to talk about the test. I'm going to put these formulas up on the board right now, and I just want you to write them down and think about them. There are 2 formulas associated with blackbody spectra that are important to know about. I can calculate the brightness of a light source based on its temperature, only if they're black bodies. So a black body is a hot, dense solid, and it glows due to temperature alone. Sometimes I use the key phrase to help students. I glow because I'm hot. That's what a black body means. And you can calculate the wavelength, the peak wavelength that's going to emit, and you can calculate its brightness using 2 famous formulas. The so-called Stefan-Boltzmann law. It basically tells you how much light an object like a star will emit. The brightness is a new constant of nature called the Stefan-Boltzmann constant times the temperature to the 4th. Now, for those of you who don't speak Greek, this letter here is called sigma. Sigma is like a little O with a cap on it. And the Stefan-Boltzmann constant is 6 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th. There is also Wien's law. Wien's law tells you the peak wavelength emitted by a black body. Lambda max, the peak wavelength of emission, is 3 million nanometers times kelvins divided by the temperature. Taken together, these two formulas can be used to great effect to calculate the quantity of light that comes from a hot object and to find out what its peak wavelength is. Normally, I would like to introduce some sample problems here, but I'm kind of out of time because I've goofed off with you guys today, which is always fun, but always bad. So I'm gonna leave the sample problems to our office hours section on Tuesday, correct?
Sure.
All right. I hope everyone's paying attention now because I'm gonna talk about the test. Does everyone have these notes down? Look at, not everyone's sharing, which is fine, I guess, but it's harder to tell who's, okay, you guys are all thumbs up in me, that's great. All right, here I go, erasing. All right, let's talk about the exam. I know it's a source of stress, I got plans for that. The exam is going to be 100 questions, and they're gonna be multi-choice. Each question will have 5 possible answers. That means you have a 1 in 5 or a 20% chance of randomly guessing the right answer. You should be able to score 20 points on this test just by filling in some bubbles, okay? Anything over that is stuff that I taught you, hopefully. Now, there are 3 sections. There's a section with diagrams. In the diagram section, I'll show you something that we've studied in the class, and I'll ask you to define the vocabulary term associated with it. Question 1 is this. Question 2 refers to that circle. Question 3 refers to that line, or that point, or that coordinate. Coordinates. They might show up on your test. Okay. So, and then you'll have to identify the appropriate term. This is supposed to be kind of one of the easier sections, but you do have to know some stuff. There'll be maybe 5 pictures with 6 questions each, or something like that. Roughly 30 points worth of diagrams. Then there's a section, also 30 questions or so, that's kind of general multiple choice test questions. Here, I might ask you a factual question like, what is Kirchhoff's second law of radiation? Or what's Newton's first law of motion? Or I might ask you to do small math. Usually these are non-math, but they do have some small math. Like you might have to multiply 2 numbers or something like that. But usually they're less involved problems. Maybe I'll ask you to calculate the wavelength of a photon or something. In the 3rd section, we have applications. The applications are the math questions. I'm going to give you some problem where I give you Jupiter has a period of 11.2 years, and I give you some other information about Jupiter. And then you're going to have to do, you know how like our homework questions, we usually have to break them down into parts where we do a unit conversion, then we plug into a formula, and then we compare. It'll be just like your homework problems. You'll have some givens. You'll have to first do unit conversions. Then you'll have to find a formula to plug it in. By the way, would you guys like a copy of the formula sheet that you're going to have on the test? I almost forgot to mention that. And
yeah, please. I figured you already had it up online, but yeah, that thing is great.
I did not think to do it until just now, and I'm so glad I did because
yeah, that's huge.
That's totally huge. This is the 2nd formula sheet. Let's see here. The 2nd formula sheet has more formulas than you need. Let me see if I can, I want to show you it exactly as it's going to appear on your exam so that you're kind of familiar with it the way you would be with an old glove or something. Yeah. Okay, let me save this. This is AS1020 midterm formula sheet. And let me, I think I can select and then invert my selection. That would be kind of nice. Can you invert the selection somehow? All right, let's just try it the old-fashioned way. I'm gonna just quickly delete everything. Hold on, guys, this takes a second. Now, some other things I want to say about how we're going to do this midterm exam. You know, I understand that taking an exam is stressful in the best of times. Doing it online is probably going to be quite awkward. Normally during one of my tests, you are not allowed to use notebooks, but all right, here we go. So this is just it right here. Save. You guys ready? I'm going to put this into the chat window. Everyone go into the chat window, file, my computer. There we go. Do you guys see that? Did that go to your chat window?
Yeah. Yep.
Okay.
Nice.
That's something, you notice it has the constants and it has conversion factors. Honestly though, even though normally during a test I only let people use the formula sheet, you're going to be doing this in your rooms, and I really don't want to police you, because I think policing is lame, and I think trying to watch to see if you're cheating is lame. I think the test is tricky enough and you're having a limited time. It's going to be a run for your money. It's not something that's going to be, if you can figure out how to cheat on this test, then that is its own sort of cunning, and that should be rewarded on some level. So what I'm going to say is we're all in this together in some way. And if you want to use your notes or notebooks, I'm not going to stop you. In fact, I'll probably be logged in with you. And I think the way we'll do it is we'll all mute, including myself. I'll mute as well. And I'll just be kind of bitty-bopping around my apartment. Maybe I'll dust the books or read a book, or maybe I'll finally grade all your papers or something. But I'll just be kind of hanging out in the background. And if someone has a question, normally people can kind of come up and ask me a question one-on-one. But maybe the whole group can hear the question in case it benefits them. So like if Will or Jose had a question, they'd unmute and they'd say, Brennan, I got a question. And I'd say, yeah. And they can show me their paper and say, I'm working on problem 27, but I feel like I'm missing something, or was I supposed to use the radius? They can ask me whatever they can ask me. And I will try to give you a hint. And everyone else can kind of eavesdrop on that hint in case it applies to them too. I don't want to turn it into a Wild West free-for-all, but you should have access to me, because sometimes a small hint can make a big difference with a bunch of points, and I'm happy to do it. Also, I can clarify it if the wording is confusing, or every now and then I forget to give you a formula or something, or an equation. We already talked about the office hours session and how important that's going to be, right? I'm basically going to be going over a dry run of the test beforehand, at least the math questions. My ability to cover those questions will depend upon how good you are. So if you don't know how to do dimensional analysis, we'll get through like 2 questions. If you know how to do a few things, we can get through maybe all of the questions, and you'll basically get to see how I would want you to solve the problem before you have to go solve it. I can't imagine the only thing I could do better than that is actually take the test for you, and that would be unethical, right? So, okay. We're going to do a very, very quick lab today, because I cut really far into our lab session. I just want to show you guys a couple of spectra. Oh, by the way, is everything clear about the tests, the questions? I'm sorry, the chapters we're going to be covering? Chapters 2, bits of S1 and 3, Chapter 4 and Chapter 5. Basically, all the stuff in your notebooks, that's what we're covering. And a great way to study for the test is to redo your homeworks, okay? Redoing your homeworks is the pound for pound most effective way to study for the test. Also, looking through my notes, I asked one of my students who got like a 98 on my test before. I said, how did you do it? She said, first I redid the homeworks, and then I looked over all the notes that you gave me in class. If that worked for her, maybe it'll work for you too, okay? All right. Did you guys have a printout of the spectroscopy lab? The spectroscopy lab will require us to use some colored pencils if you have them. If you don't, you can use a pencil and label the colors, but that's kind of less cool if you ask me. The sheet looks like, oops. No. It looks like this. Do you guys see this? Okay.
Printing it off now.
Joel, can you say that louder, please?
The one that's asking for the gas name?
Yeah, I'm going to give those to you, okay?
All right, let me print it off.
I'm going to print, yeah, I'll print mine out right now.
Yeah, I'll kind of move over here to the, actually, I'm going to stay here for today's lab. Well, what am I going to do?
Actually, what's hey Brandon, what's the number at the bottom of that page? Because I still have my lab book. I'm pretty sure I have that. I don't have to print it.
You probably did this last year. It's 11-5.
11-5. Okay, I'll see if I have it.
But if you had your lab book last semester, you definitely did this.
Oh yeah, got it. No, but you printed all of them out for us then too. So I have like a whole lab book now, like truly with everything in it.
That's nice. That's actually nice. All right. As to the gas names, I think we're going to do sort of less than usual because we don't have a ton of time. Let's try to do hydrogen and helium and then maybe a light bulb in the solar spectrum. So our gas names, we'll try hydrogen, helium, light bulb, and solar spectrum. We'll see if we can get through that. All right. Now, the name of the game works like this. If you have colored pencils, do I have colored pencils? Hold on.
Will markers work?
Yeah, he just wants us to differentiate the lines.
Okay.
Brandon, you better have colored pencils because you gave me a hard time earlier about not having colored pencils.
I was so sure that I didn't. Unfortunately, someone gave me the lamest box of colored pencils. They gave me these colored pencils, which, of course, I'm going to want the Roy G. Biv spectrum, but these are like some lame-ass pastels. I don't even think there's an indigo in here. Let me see if I can find some real ones. I thought I had them ready to go, but now I'm not quite so sure. I can't believe I'm going through this again. Thanks a lot, guys, for the peanuts. The peanuts are really helpful.
We need to go back to the dog park. Huh? Yeah. Long days, huh? Long days.
Oh, this place is so dumb. Oh yeah. Oh yeah. Okay. Well, I found some oil pastels. That'll be the next best thing, right? I just need to open them up. Okay. Well, it'll have to do, right? Do you guys, did you find some colored pencils of some type? If you
I have
can't
no
find
color.
colored pencils, can I make a recommendation? What you could do, Joel, check me out over here. You could open this up in some kind of a paint program, or maybe even Zoom. And when it comes time to make the lines, you could kind of 656, hydrogen, you could draw on a red line here, right? And you could put in like a blue line over here, right? You see what I mean? That's one way you could do it digitally, putting a violet line over here. Think you can pull this off one way or the other? Worst comes to worse, you know what you could do? You could just draw it in with pencil and label the colors. That's the least cool option, but I'll accept it. Does that sound cool?
Sure.
All right.
I'll make it work.
Let's see if we can observe hydrogen spectrum. We already kind of know what to expect, but let's look at it anyways. This is going to require everything to work perfectly for me to be able to share my screen with you from my phone. Okay. All right. We're going to do hydrogen first, right?
Yep.
Let's see if we can take a photo of it. Hold on. I need some light in the background here. So I got some background light so I can. Okay. Do you guys see all those background photons? Those are contamination. Let me see if I can get a cleaner photo of this. Whoa. What the shit? Why is it? Sorry. That one came out decent enough, right?
Yep.
Okay. So it's not the same as looking through it, but you can see around 650 we have a red line. You want to put that one down? By the way, notice that your labs are doing this in angstroms, right? So, you know what? I am going to have to, I'm going to bring the computer over here with me. Okay. So, here I am. Get my colored crayons out. So this is actually orange, not red. That's irritating. Here's a red photon. Now these are in a unit called angstroms. So the way this works is 1 nanometer is equal to 10 angstroms. We saw our red line at 650 nanometers. That's 6,500 angstroms. You guys got that? I'll assume that's a yes.
Yep.
How about the blue line? It's a little fuzzy, but that's 400 and that's 500. The line in the middle is 450. 460, 470, 480, we see a blue line. So somewhere here around 4,800. So this is 4,800. That's where we'll put a blue emission line. Everyone following me here?
Yep.
And now you guys might be wondering, well, Brendan, what about all those green and yellow emission lines? Unfortunately, one of the difficult things about hydrogen is it's such a light and volatile gas that over time air contaminates it. And so you're seeing the spectrum of air superimposed over it. I want us to, one of the hydrogens I have is good and doesn't have air contaminating it, but I picked the wrong one when I was on COVID watch and I just grabbed a bunch of stuff willy-nilly from the labs. Now the last photon, the hydrogen gamma, you can actually see, do you see how it's a little bit of a darker purple right there? The photograph is really fuzzy, but it looks like 410, 420, 430 nanometers. I also kind of know where it is. So we will take a purple photon. Where's my oil pastels here? Oh, this place is turning into a real dump on my watch. You'd think I'd have a purple crayon laying around. I do have a violet pastel. So at 400, this is 420 and this is 440. So 430 is in there somewhere. And there's our spectrum of hydrogen, a red line, a blue line, and a purple line. Okay? So that was hydrogen. Next up, we're going to try helium. Okay?
Yep.
All right. So that's probably wicked hot. Remind me to turn these off when we're drawing the lines in. Ooh, ow. Ow. Hey, do we have a hot mitt? I really miss my lab tech here. All right. Thank you. Guys, can you hear me? Students?
Yep.
Yeah.
Are you still seeing this? Can you see my screen?
Yep.
Look at how orange the helium lamp is. Woo! That's bright. Okay. Are we ready for the helium spectrum? Yes?
Yes.
Yep.
All right. By the way, you might be able to see me if I move the chair. It's kind of nice to have me in the background window so that you can kind of see, like you're seeing my phone shake around, and I know that's really irritating, but just bear with me. I want to check my field of view on the camera. You guys can see me kneeling down over here so you can see what I'm up to in the small window. You know, I probably could have set this up a little more professionally, but you get what you pay for, you know? And unfortunately, you paid for me. All right.
Well, if you weren't so busy feeding the raccoon, I mean, come on.
So we can see some lines in there. Do you see that bright yellow line?
Yep.
Well, I'm going to take a picture from far away, and then I'm going to try to zoom in, but I have to kind of hold multiple things here, so. This one's coming out pretty good, actually. Hey, not bad, huh? Hold on. I think we can make this even better. I can't believe this is working as well as it's working. All right. What do you say we go with one of those? Guys, I do have a set of colored pencils somewhere. I remember right after I did this lab, I took them out and I found them. But now, wait. Is this colored pencils? Holy shit. Guys, I think I just hit colored pencil jackpot. Look at this. Watch this. You see that? It looks like paints, but look at this. Ooh,
Oh.
look at that, huh?
Right.
I am shitting in high cotton, as they say. Okay, so what colors?
There's cyan and indigo.
Look at all that. The whole thing. That's how you do it, right there. Okay, this is what we need. How about underneath here?
That's classy.
Isn't that class? You know, I probably bought it at Job Lot. But, oh, pastel. Look at this. I probably never even used this. Not one damn time. Well, apparently once, because one of the markers is missing. That kind of shit really bothers me. Okay, what colors do I need for my helium spectrum? Red, yellow,
Green and indigo.
yeah, so I need a red. I hope these are sharp. I've never actually taken these out of the box here, so. Oh yeah, they're all sharpened up. Oh. A red, you said I need an indigo? We got a great indigo right here.
And a green.
And a green, blue, a violet. couple of greens. All right, just get the whole fucking armada over here. Wow, do you know how awesome I feel right now having discovered those colored pencils? Look, fuck these guys. All right, sorry, I shouldn't say that. I'm not going to say any more dirty words on camera. Okay, so let's look at our spectrum together. It looks like we've got a red line. So what would you guys say the wavelength of that red line is?
Like
660, yeah?
Yeah, because let me see if I can, let me get my mouse here. This is part of learning how to do science, is learning how to read the graphs. Now, can I draw, if I'm drawing right now, can you guys see that?
Yep.
Yes.
Okay, cool. So this is 600 right here. That's 700, and that's 650. What is each major tick mark worth? What are these big tick marks worth?
10.
Yeah, and little ones are 5. So that's pretty much 660. What Shay said, I should have just, I didn't have to question it. So now, on my phone, if I do this, it's kind of frozen. What I don't understand is my phone is showing like my paper. Why is it stuck there? That's what I don't get. Oh,
Because
okay.
the iPhone's not playing well with others.
Yeah,
There.
exactly. All right, here we go. So I'm sorry, that was a red line at 660. So now this is in angstroms. This is what, 6,200? 6,400 angstroms. 6,600. There's your red line, okay?
Mm-hmm.
We have a yellow line. What would you guys say the wavelength of the yellow line is?
58.
580.
Oh wait, yeah, other way.
Yeah, other way. Try again.
580.
580 sounds good to me. So I'll take a yellow crayon now. And 580 would be just before 600, right? What else? Looks like we have like a teal, maybe 2 teal lines, one at 500 and one at 490. Do you guys see that?
Yep.
We'll even try to represent them as brighter and dimmer. We'll try to represent the line. They call it the line strength. So this one's sort of at 500 and at 490. Well, I meant that one to be dimmer than the other one, but I didn't do a great job of that. That looks pretty darn indigo, wouldn't you say?
Mm-hmm.
Yeah.
What's our wavelength?
440.
Yeah. I'll buy that. All right.
Oh.
410, 440. Okay, here we go. That's a nice indigo color. Wow, these are classy pencils. These are really gourmet. You know, I think I bought this for an ex-girlfriend and she didn't take it. So it's kind of like a present to myself, you know what I'm saying? They're mine now, that's all I know.
You're doing the raccoon voice again, like Joel said. It sounds evil. Like, you're mine.
You're mine.
Creepy. Creepy.
So normally I would have you do a lot more elements, but I dithered and I lost a lot of time looking for markers and stuff. I think we should look at the incandescent spectrum, the light bulb, and we should look at the sun spectrum. So first let's try a light bulb, okay? So here I have a good old-fashioned lamp. And in this lamp, I was going to use it for the inverse square law. I have a white light bulb, just a simple white light bulb. Let's see if we can't get the spectrum. And let's see if we can be quantitative about it. Put this over here. Put this closer to here so I can get some of the background light. I haven't tried it on this light source. Hopefully this will work okay. I'm just lowering that so it's sort of at the same height. I'm resting the spectroscope here so I can stabilize it. Let's get in there. Oh, wow. You guys see that? Whoa.
Yep. Oh, that's
God damn it. Oh man, I just had it so nice.
Yeah, you got it. You got it taken. You captured it.
Wait, it looks like shit though. There we go.
Check out the first one you took.
Yeah, that was a video, unfortunately.
Oh.
I think it was a video, right?
I don't remember.
Yeah. Yeah, I was stupidly on the video. God damn it. Hold on. I think my finger swiped it to video. I'm almost there. Hold on.
If worse comes to worse, you can just screenshot the actual video if you can't figure it out.
What's that?
If you took a video of it and that's like the only time you were able to get it perfectly, you can just screenshot the video and just pause it or something if you can't.
Yeah.
Well, seems like you got it now.
I mean, I kind of know it by heart, but the point is to explore it yourself for the first time. This one picture came out probably the best. Let's try this one. So this picture here looks like orange goes just past 600 to about 610 or so, right? So I would say red. By the way, the name of this spectrum is the incandescent. But the idea is that the incandescent bulb is basically a black body. It's the same as a black body or a continuous spectrum. So around 610 or around 620, red starts, but did you guys notice that it wasn't emission lines, but it was like a smooth band of red? This is very important. A black body spectrum does not emit lines. It emits a swath. It basically emits every single wavelength in the red spectrum. This is what makes continuous spectra different from emission line spectra. Next, we had orange. And orange kind of went from like 590 up to about 610 or so. Okay. And yellow is actually quite narrow range. I don't know, what's that, a picture of my ceiling or something? Right. Yellow, you probably didn't capture it, but yellow is a super, super narrow range. Like that's 550, the big tick, 560, 570. It maybe is 575 to 585. It's pretty damn, yellow is one of the tiniest bands there is. So it's we'll just kind of cheat. So this is 560. We'll put the yellow in there, 565 to 575. So it's kind of the right feeling. Notice that green, however, this is the best one I got. Green goes from like 6. Part of this is an artifact caused by the CCD. That that right there is 6.
575.
Oh yeah, sorry, 560, 575 or so, just where the yellow starts. But notice that green goes all the way to teal is around 500. Just to keep things simple, do I have a better teal now? I guess not. Sort of gets teal by 500, but we'll use green. We'll use a sunny green at first, like a kind of chartreusey green. And because I've got these mad cool colors, I'm going to go to a deeper green. One shade of green is fine, but I don't know if you guys are able to reproduce this at all. I got lucky finding those crayons, you know. So this is sort of what the solar spectrum looks like. Joel, where would you say that blue ends and indigo begins? Kind of hard to see the numbers here, but.
Like 470?
No, this is, oh yeah, sorry. Yeah, 470 to maybe 440. I'd say 440 to 470 is indigo. Very good, Joel. I'm sorry. I was having a braineurism there. So here's my indigo. Wait, so first I'm going to do cyan. I'll do a nice cyan color all the way to about 470 or so. And then I'll switch over to dark indigo. Indigo's like 440. Maybe this is an even deeper indigo. And then eventually it turns violet. Violet's like 400 to maybe. Cool. Oh, shit. Guys, you know what? Look what I did. Students do this all the time. I put it below the incandescent. That's okay, though, because guess what? The next spectrum that we're going to do is the solar spectrum. Now, in anticipation of the solar spectrum, I want you guys to do the same thing again, because the solar spectrum is going to be kind of like a rainbow with one little twist. So if you've made a rainbow with me, I want you to copy that rainbow again. This ought to help you memorize the wavelengths of light, too. Vibgyor, violet, indigo, blue, followed by green. Green's a very wide band. Followed by yellow. Followed by orange. This is kind of a fun Bob Rossi kind of lab here. And then followed by red. If you guys can see what I'm doing. You know, lab is kind of like arts and crafts. It's like about making stuff. And that's kind of cool. So for now, your incandescent spectrum and your solar spectrum should be looking about the same. Can you guys see that?
Yep.
But there is a difference. Do you want to see the difference? Say yes.
Yep.
Yep.
All right, here comes the solar spectrum. I'm going to take this to the window. Let's see if I can get some sun. We don't have to stare directly at the sun. We just need to stare at like the blue sky.
Interesting.
Yeah, right? I remember this in the last lab. Cool.
Like the orange and yellow almost like disappear.
Wait, do you see the absorption lines? Look. Wait. Shoot. This requires acrobatics because I have to be able to hold the spectroscope and the phone at the same time. So it's quite difficult. Hold on.
And take a picture.
It's very difficult. Yeah, hold on.
Yeah.
And focus it with my thumb at the same time. I want to get you those absorption lines. So tough, guys. But on a couple of them, you can just barely see the absorption lines. Let's see if we can find them. Can I be honest? When you look at them with your eyeball, the absorption lines are really, really obvious. What's happening is the CCD is having a contrast issue. It's trying to focus on the numbers and on the colors, and the absorption line is so much more dim that the cheap CCD in this phone doesn't have enough dynamic range. I bet on Jordan's camera it'll look better, but I'm going to just see if we can kind of wing this, okay? Because we're getting to the edge of our rainbow here. And I mean that as a pun as well. Can you guys see there? You can just about see those faint absorption lines in the green. Can you see them there?
Yeah.
You can just about see them here and here. You really don't have to try that hard to see them when you're looking at it. But part of the thing is we're kind of using a cheap CCD camera. Oh, you can definitely see that one. Let me clear all this out again. Can you see that one right there?
Yeah.
They all appear pretty even too.
Yeah, they're in reality, they're spaced out all over the place. If you use a high resolution spectroscope, there are thousands and thousands of them. Some are thick, some are thin. I actually have a really, really nice spectroscope, but there's reasons why I don't want to set it up for this lab because it's currently configured for my telescope and I'm doing a major science. I'm actually doing spectroscopy at our telescope with a Brown professor. We have a spectrograph that we attach to the telescope and we're measuring the velocities of binary stars right around hydrogen alpha. So my spectroscope is currently configured to be in the focus of my telescope, and to make it focused for a student demonstration, I'd have to adjust the lens and it would screw up the science project. So I kind of want to show you, but I kind of don't all at the same time. Basically, if we did look through it, we'd see something like you saw in that lab today with all of those lines. Let's go ahead and let's fill in the dark absorption lines. All we're going to do here is we've already made the spectrum. And just to make the solar spectrum legitimate, we're going to take a black number 2 pencil. And we're going to draw on a few of the absorption lines that are well known. So we could see that there was an absorption line kind of in the boundary between the yellow and the orange. We know there's one in the red near hydrogen alpha. Sorry. So these are just the absorption lines. We could see a couple in the green, right? And at least one in the blue. So we're just drawing a few of the dark absorption line spectrum. The importance is that these two are different types of spectra. This is absorption, and this is continuous, and these up here are emission. So it's a cute little lab because you can see the 3 different types of spectra just by looking at some fun blinky lights around the room. Everyone feel like they got that? I wanted to keep this one short today. I guess I went right up to 4. It's hard to do anything on time these days, especially when you're me. But although it's not as many elements as I would have subjected you to in a real lab, with all the bullshit and the goofing around, I think we did a good enough job. So you guys can just submit that to me, okay?
I have a question about what the gas name for 3 and 4 are.
Yeah, even though it says gas, these are not gases. The incandescent, let me share with you again. I don't know if my phone is going to allow it. Sorry. Can you read that okay,
Yep.
Evelyn?
Thank you.
Have you ever heard that word before, incandescent?
Yeah.
It means a filament is being heated up. It means light through heat, essentially. And then the solar spectrum means the spectrum of the sun. Does that solve your problems? Well, does it solve your lab problems?
Not all my problems.
So Brendan.
Yep.
What would it look like if we did a LED?
Great question. In fact, I thought about asking you the same thing. Would you expect it to be emission, absorption, or continuous? Take a guess, and then I'll show you.
I know I shouldn't have asked this.
I'll
think.
tell you. Do you know what LED is for?
Probably like a continuous.
Well, you'd think so because LEDs are trying to mimic white light. But what's so freaking cool about LEDs is they're not actually black bodies. LED stands for light emitting diode. They're getting atoms to emit particular wavelengths of light, but they're getting them covered in the blue, in the green, and in the red, and turning them into a false white. So to do this, I'm going to give a demonstration, but I'm going to need to borrow one of the gal's phones for a second. Now my phone isn't mirroring. I was afraid of this. Come on, baby. Oh, I know what's going on. I didn't share screen. Share screen. Boom. There we go.
Can you do it off your iPad?
Oh yeah, I could, or I could probably. Let's see if I can get the iPad. Hey, can I borrow one of your cell phones for 1 second? You just turn the light on, and yeah. So just activate your flashlight, and then I'm going to take it over there. Okay. So you guys know that these are powered by LEDs, right?
Yeah.
So this is a great question, very relevant. There goes the sensor. Okay, so let's grab my spectroscope. And so you guys see that?
Yep.
It looks continuous at first. Get out of here. But it's mimicking continuous spectra through an emission line. It's a cool hybrid in a way. Your question is it looks, first of all, I gotta look through myself with my own eye. Actually, guys, they've done such a good job on some LEDs. All right, that's not what I was expecting. I've got to be honest with you. Jordan does have one of these fancy iPhone 10,000s though. So here, Jordan, I don't want to kill your batteries. So listen, on some of the cheaper LEDs, what you will see is you'll see like a big band of red, a big band of green, and a big band of blue, but they're kind of segregated. So they're like they've taken an emission line, but they've stretched it out. I was expecting to see that. I was expecting to see the spectrum of the LED have like a block of red, a block of green, and a block of blue, so that they would kind of artificially fake light. But these new LEDs, they're getting atoms to emit specific colors, but then somehow they're like getting them to shift their energies so they can create a perfect rainbow. When I looked at her LED, I was expecting to see a block, and a block, kind of like 3 bands. It was a perfect rainbow, completely indistinguishable from an incandescent source. But I know that LED is not being powered by heat. It's, for instance, if you turn your light on in your phone, you don't feel any heat coming off the thing. It's an LED light, you know?
Mm-hmm.
I'm going to talk more about them at a later date. Won't do it now.
Okay.
Because I'm out of time. And I've taken enough of your day. But we have a plan. So, guys, everything that we've learned so far will be on the exam. And the most important thing is 10 a.m. we do some sample problems, and we'll take the test from 12 to 3. Somehow the test will be administered online through Blackboard. That's my job this weekend to figure it out. But what I'm hoping is that you'll be able to just click the answer, and then somehow it'll collate the scores for me. If worse comes to worse and I can't figure it out, I might have to just send you a Microsoft Word document, and you might have to highlight the answers and send it back. I'm hoping it won't be that low tech. I'm hoping it will be slicker than that, but we'll see, okay?
That's what all my other teachers had to do. I mean,
What'd they do?
That's what last semester was. It was like print it out, circle your answers, and take a picture of them and send them back type deal.
Really? I'm going to see if I can do it a little more sophisticated than that. We should be able to administer. Has anyone taken a class where they had a multiple choice test where they had to click answers? That's what I want to figure out how to do. You did, Will?
Yeah.
There you go. Yeah.
All my quizzes for criminology are like that.
Okay, Catherine says all of her tests are on Blackboard. All right, guys. I had an awesome time with you as usual. Are there any other questions, or do you know what to do? Turn in today's homework, turn in today's lab, study your homeworks. Email me if you have questions. I'll answer you.
Was today homework 4?
Yes.
5.
It was homework 4, but weirdly,
4,
Lab 6. We kind of leapfrogged over Lab 5.
Yeah.
So when you submit, Jose, homework 4, but Lab 6.
I don't see homework 4 here, though. I see homework 3, then it jumps to homework 6.
Yeah, it's all the way down at the bottom.
Oh, I forgot to. You know what? I couldn't move it up. Hold on.
Oh, okay. I see it now.
Yeah, there you go. Yeah, it's all the way down at the bottom.
Oh, okay.
You know what happened, guys? That day, Blackboard glitched on me, and it wouldn't let me. Whenever you start a new assignment, it puts it at the bottom. They wouldn't let me move it up, but now they're letting me move it up. So I'll slide it up, and you should see that reflected. So, Jose, hold on a second. It's about to change slots. Oops. Now it's before 3. Hold on. Okay. Do you see it in the right position now? Refresh your screen. Yeah. Sorry about that. It won't be at the bottom anymore, everyone, okay? All right. Let me just check the chat. Yeah. Catherine, I'll work on the test. I'll see what I can do to make it clickable. That'll be easier for you guys. And remember, it'll be a team effort. I'll be here. We can all, if everyone's cool with it, we'll all stay on mute. And when someone has a question, they'll unmute. They'll say, Brennan, got a question. I'll answer it to everyone so that everyone can see what we're talking about. And that's actually kind of helpful because sometimes students will catch an error or a mistake, and then everyone should know about it, okay? All right.
Don't forget to pay your cable bill.
I actually did that. That's why I was 5 minutes late after the break because I was worried that I was going to go off. Thanks so much. All right. Bye, guys.
Don't forget to read the raccoon, too.
All right, I will. We're going to check on him. Adios, amigos.
Bye.
Yeah.